Okay, so shall we start the afternoon session? Okay, I think we can now start. And so first speaker of this session is Junseok Lee from Tohoku University, and he's going to tell us about the evolution of the domain world network with inflationary fluctuation under the asymmetric potential. So please start.
Thank you for thank you for introduction. I'm Lee from Tohoku University, and I'm very happy to have a chance to talk to you. Today, I'd like to talk about the evolution of the domain world network with inflationary fluctuations under the asymmetric potential. This talk is based on the collaboration with Kitajima-san and Takahashi-san and In-san from in Tohoku University, and the paper is in preparation. As Diego already explained in the previous talk, the domain world is a type of topological defect that can be produced when there are disconnected degenerate vacua. For concrete discussion, we assume the G2 phase transition like this. In the universe, each Hubble horizon contains order 1 sheet of domain world known as the scaling solution. It can be seen in many previous works. However, this scaling solution known to cause some cosmological problem. The energy density of the cosmological domain world is localized in its surface as its tension. Scaling solution implies that each Hubble volume h to the -3 contains the domain worlds with the area of h to the -2. This implies that the energy density of the domain worlds are proportional. The domain worlds is proportional to the Hubble parameter. But this decreases very slowly compared to the other energy components. For example, in the matter-dominated universe, it is proportional to the scale factor a to the -1.5, while the energy density of the matter is proportional to the a to the -3. So domain worlds easily can become dominant or subdominant energy component of the universe. This is inconsistent with the isotropy of the CMB observations. This problem is called the cosmological domain problem. To avoid this problem, we need to require some small domain world tensions up to a few up to the order of a few MeV cubed or bias which can make the domain world unstable. So there are two methods to destabilize the domain world. And the first one is initial population bias, which means that there is some shift of the mean value of the initial distribution from the potential hilltop. And the second one is potential bias, which means that there is some slight energy gap between the two vacua. It makes the pressure that leads to the collapse of first vacuum. And there can be the two distinguishable initial conditions. This two figure is what Diego wanted to show in the previous section. Yeah. The left one is shows an example of fluctuations with no large scale correlations. This corresponds to the thermal fluctuations, And the right one shows an example of the fluctuation. Scalar invariant fluctuations, which can be realized by the inflation of the universe. For instance, the CMB temperature distribution pattern shows very similar features with this. So now we have two different initial conditions and two kind of bias we can impose. Let's consider the time development of the domain where under each bias from each initial condition. Many previous works have studied the stability of the domain where networks and found that it collapsed quickly under either the population bias or the potential bias with thermal fluctuations. In the past, it was concluded that the domain where networks produced by the initial inflationary fluctuations is also unstable. This belief has been held for about 30 years. But they didn't properly incorporate the initial inflationary fluctuations numerically. So, and now we saw in the previous section that even under the population bias, initial inflationary fluctuations can produce the domain where networks with a dramatically long lifetime. So this stability of the network makes us to adopt about the instability of this instability under the potential bias. Therefore, we studied on this case. Let me introduce what we did. This is the first study on the evolution of the domain where network under the potential bias based on the lattice simulations with initial inflationary fluctuations. We generated random numbers on the momentum space so that the fluctuations have scale invariance, and Fourier transformed them to use them as the initial conditions. And we introduced the linear bias term in the potential and solved the Klein-Gordon equation on the lattice. To evaluate the lifetime, we focused on the ratio of the volume of first vacuum domain against the total volume of the system, because it was more convenient rather than the domain or length data. This two-figure shows the time evolution of the volume ratio with the summer fluctuations and the inflation fluctuations. The lower lines are more biased. The dotted lines is the fitting in this function form. I used it for fitting the data after the network was constructed and the decay started. So as you can see, they follow the same decaying pattern. And this figure shows the we investigate the bias dependency of the lifetime. This figure shows that the horizontal axis represents the bias parameter epsilon, and the vertical one is the lifetime tau decay. And the solid line is a fit in power function like this. I use the less biased 3 data point because if the lifetime is too short, then there can be an unintended population bias when the network is about to construct it. The fitting of the two cases showed the same power dependency of minus 0.6. We can predict roughly the bias dependency by this equation, which means that the domain will collapse at the timing when its pressure starts to overrun its energy density. Yeah, in the radiation-dominated era, this implies that the tau decay is proportional to the epsilon to the minus 1/2. So our result is almost consistent with the rough estimation. As I mentioned previously, this result is quite different from the population biased case. And the left figure shows the development of volume ratio, which is one of the results of the work carried out by collaborators, including Diego. Yeah. So this means that there are some essential differences between these two bias. So the large scale correlation implies that no matter how large a scale you look at, there must be a large void. I mean, for example, larger than the Hubble horizon scale. Under the population bias, these large voids act as an obstacle to domain words collapsing and merging by its tension. So these large minor voids are comparably stable with even with its tension. On the other hand, under the population bias, the large first vacuum voids shrink totally. It's because of the existence of the tiny true vacuum like this. These bubbles are scattered in various places in the voids, and they can grow up in this case. So finally, the typical distances between the words is important, become important factor to determine the lifetime. So we investigated typical domain word distances. This figure shows the histogram of the domain word distance. The horizontal axis is distance regularized by the Hubble horizon, and the vertical one is normalized frequency. What this figure tells us is the typical distance between the words is almost the same for these two inflationary and thermal cases. On average, order Hubble distance, So this is our conclusion. We studied the time development of domain word network under the potential bias with initial inflation or fluctuations, and we found that the lifetime is the same as the thermal case. So if there are some slight energy gap in the two vacua, we can the cosmological domain word problem is avoidable. Before I finish my talk, let me introduce the relations to the axion. Yeah, the axion or the axion-like particle is a good example for the applications of this setup. The breaking of the peptide in U1 and the inflationary fluctuations leads to the formation of the axion domain worlds. It is well known that the collapse of domain worlds can produce the dark matter axions. Considering the coupling with the photons, the axion domain world gives implications on the anisotropic cosmic birefringence, which is already talked in previous talk. Yeah, that's all. Thank you for listening.
Thank you. Thank you very much. Is there any question or comments? Any? Let's see. Oh, yes.
Thank you very much. So I have a naive question on the when you numerically simulate the domain of information. So depending on the initial condition, so thermal or inflation fluctuation, is there any possibility to form a kind of oscillons which might constrain in the history of the universe?
Sorry, I'm not. I'm not good at oscillons, but in our simulations, the oscillon was observed in our simulations. So we want studied about the more for
Okay.
yeah.
Thank you.
Ongoing, yeah.
Any more comment? Yes.
Yeah, usually, yeah, for the cosmic birefringence case, we assume that domain world energy density is small. And if there is oscillon formation, but oscillon energy density is even smaller than the domain world, therefore, it is safe. Thank you.
We still have some time. So do you have any question? Any question from the Zoom audience? I need to check. If not, we can move on to the next speaker. Yeah, thank you very much.
Oh.
この参加者に自分へのコネクションを切れば、はいはい。インターネットしたら。Sorry, I'm very sorry that apparently we have a technical problem again. So the participants here, please turn off your internet. So probably the reason why we have this technical problem is the internet connection here is very weak. So on-site participant, we can see the slides by our eyes. So please, log off from the Zoom, and if you can help us, please stop using internet connection. Probably that helps. Yeah, that's improve the situation. We hope. とりあえずなんかインターネットのつながりがすごい弱いんで、あんまり使わないでほしいです。部屋にいる人。あと、ズームからも出てほしいです。なんか今、ズームに入れなくなってるそうですね。
なんか、そうなんですよね。ズームだけは最後までいくんで。はい。
Sure. I'm spelling slowly, but let me.
Can you hear me from the Zoom participants? Yes. Okay, so thank you for kind introduction. My name is Fumihiro Naokawa from the University of Tokyo, and today I want to talk about the weak gravitational lensing effect on cosmic birefringence. So first of all, I want to talk about the motivation of this work. And the cosmic birefringence is a newly reported very interesting signal from simple polarization, as Gonzalez and Leeson mentioned today's talk. And the interesting point of this phenomenon is its parities are violating. And so we can assume there's something new physics behind that. And the most probable origin is axion-like particles. And fortunately, there are several next generations simple polarization observations across the world. So to make the more sophisticated data of cosmic birefringence, we also have to improve the precisions of theoretical prediction. So Okay, so we focus on the weak gravitational lensing effect. This effect is a very crucial factor for precise observation and theoretical prediction of CMP. And it is especially important for the next generation ground-based observations because this effect can significantly affect on the small scale of CMP. Okay, so so several talks it appears, but first of all, what is cosmic birefringence? I'm showing the very famous CMB observation data by Planck satellite here, and as you know, the color bar denotes the temperature fluctuations, and these line segments denote the polarization direction and strength, and so. Today, I want to focus on only polarization direction, and it is difficult to recognize all sky. So first of all, I want to focus on only the limited area like this square. And here, I prepared the schematic pictures of the limited square area, and I only focused on focusing on the polarization direction. So I excluded color scale other things. So in the normal situation, the CMB photons can propagate like this. Sorry, something delaying. Like this. It's during its propagation, they keep its polarization direction. So in this case, the polarization direction distribution, which we can observe, is exactly the same things as the original distribution. However, under very special conditions, the polarization angle can rotate during its propagation like this. And so in this case, the the direction distribution which we can observe is a little different from the original ones. This is so-called cosmic birefringence. And the important point is, again, the parity violation. And as a result, the TB and EB power spectrums becomes non-zero. So I want to explain more detail about this. So we have three types of CMP observables. As you know, the temperature fluctuation denoted by theta, and two independent modes of polarizations, so-called E mode and B mode. And the temperature fluctuations and E mode is parity even component. However, only B mode is parity odd component. And so we can when analyzing the CMP data, we usually calculate the power spectrums, and when choosing the parity even and parity even, or odd and odd components from three observables to calculate the power spectrum, the left side 4 components becomes parity even components. However, when choosing even and odd components from 3 observables, the power spectrum themselves becomes parity odd component. So the right-hand side 2 components becomes always 0 when the parity symmetry is conserved in the universe. However, under the cosmic birefringence situation, these 2 components can become non-zero. And in the Leo, from the detection of EV power spectrum, it is reported that there is very tiny rotation angle in CMB polarization. Okay, so the plausible origin of this rotation is axion-like particles. Here, I'm showing the Lagrangians with standard models and axion-like particles. And in this Lagrangian, there is so-called Chern-Simons term. This is this denotes the interactions between photons fields and axion-like particle fields. And here I show the F mu nu and the definitions of F mu nu and to the F mu nu. And it is a little complex, but this B and E denotes just a normal electromagnetic field. It is totally different from the E mode and B mode of polarizations. So please be careful. And from the Lagrangian, we can derive the equation of motion like this. And in the normal Maxwell equation, the right-hand side term does not appear. But in this case, because of the existence of Chern-Simons term, there is this kind of term. And from that, we can derive the relation between rotation angle and the axion-like field value. And this is very simple equations. The variation of polarization angle is proportional to linearly the variation of ALP field value. And performing the time integrations, we can get this most simple equation. So the angle, the rotation angle of CMB polarization can be generated by the gap between the field value of present time and the field value of axion-like particles at the recombination epoch, which when the CMB photons are released. So this is a schematic pictures of the last equation. Sorry for a little Japanese, but this action, this rotation angle is induced from the this field values gap. Okay, so I show again this the last equations. And so what can we do from these equations? So we know the reported very tiny rotation angle. So we can calculate the variation of ALP field from this equation, and from that we can know the dynamics. We can estimate the dynamics of ALP field, and as a result, we can constrain on LP parameters. And this is one of the results by Fujita-san in 2 years ago. And so this, from the cosmic birefringence reported angle, we can constrain the, for example, LP mass or a coupling constant. And this, it is a little difficult to recognize, but green shaded area is the surviving area. And that was only from the rotation angle, but in the near future, there are some several next generation observations. So we can maybe extract more detailed information from the EV power spectrum itself. So we can know the exact shape of EV power spectrum, not only the rotation angle. And so by using this, so by calculating the theoretical prediction of EV power spectrum from these equations, we can estimate some, we can predict theoretically the EV power spectrum induced by cosmic birefringence. So for example, the shape of EV power spectrum can change depending on the mass or other parameters of action-like fields, action-like particle fields. And we can compare the observational one and theoretical one, and we can determine the action parameters more than just using the rotation angle. So it is very important. And this is so-called tomographic approach. And this is one of the advertisement, but one new paper is uploaded to arXiv today about this type of approach. And our today's topic is the improvement of precision of calculation, and we focused on the gravitational lensing. So what is the gravitational lensing on CMB? I again prepare the schematic pictures, and if there is nothing in the universe, the photons of CMB can propagate, defining its straight line like this. However, of course, as you know, there are some gravitational sources like dark matter in the universe. So the trajectories of photons can be deflected, like distorted like this. So as a result, the starting point which we can recognize is a little apart from the original one, like this blue arrow. So the same things happens as photons like this. So the map, CMB map we can observe is a little distorted from the original one. And this is so-called gravitational lensing effect on CMB, and this is not new effect. So of course, about temperature fluctuation, the gravitational lensing effect has been already observed, and of course, theoretically calculated. And we use so-called class. This is a public code for CMB calculation, and this class code can calculates the parity-even components of CMB, and this code originally includes the lensing correction mode for these components. And 2 years ago, this class code, last year, this class code was modified to in order to calculate the parity odd components induced by cosmic birefringence of action-like particles. And however, this modification was based on class, so the lensing correction mode is only effective for parity-even components. So we have to improve this parity-odd part, and this is our work. So we have developed the lensing correction mode for parity-odd components. Oh, sorry, this is not. Sorry, I can skip this, right? Wait a minute. Okay, so this is a result. Okay, this is a result of the calculation for our new code. The red line is lensed power spectrum, EB power spectrum, and the blue one is unlensed power spectrum of EB. So you can see the gap between the red one and blue one, especially in the right-hand side, because the lensing effect significantly affect on the shape of power spectrum in small scale area of CMB, so which is corresponding to the right-hand side of this graph. And this is the zooming up pictures of the shaded area, but we cannot recognize the shaded area. This is corresponding here, and you can recognize the changes of the shape. And maybe next you want to know is whether we can observe this effect or not in the future. And so we compared this gap to the estimated noise level of next generation observation. This is about the case of CMP stage 4, and the blue point is unlensed power spectrum, and red point is lensed power spectrum, and we added the estimated noise level of CMP stage 4 by the error bar to the red point, but maybe you cannot see because the error bar is very small. So that means the error bar is much smaller than the gap between the unlensed and the lensed power spectrum. So it clearly shows we have to do lensing correction to EB power spectrum. Okay, so the last result is we conducted a forecast of parameter search of LPs by cosmic birefringence to estimate the lensing effect. So of course, usually we have to do prepare mock observational data with lensing and theoretical prediction with lensing. But in this case, we want to know the lensing effect on parameter search. So on purpose, we prepared mock observational data with lensing and the theoretical prediction without lensing. And as a result, this is a result about CMP stage 4 in the case of 10 to minus 28 electron volt of axion-like particles. And so on purpose, we have prepared without unlensed power spectrums, and the fiduciary points we have set is denoted by red point. So the blue region, which denotes the estimated parameters, should be around the red point, but in this case, it is a little apart from the red point. So this shows without lensing correction, the estimated parameters of LPs can be biased in the future very sophisticated observation. Sorry for a little over the time. This is my conclusions. So thank you very much.
Thank you very much for the nice talk. So, any question or comments from the audience? Or from the online participants? Here you go.
So we're the most sensitive mass scale to make a difference between unlensed and lensed. So you showed the 10 to minus 28 electron volts.
Yeah.
So is there any other parameter space of the mass scale which will be so sensitive to the
yes, that's very good point. Yes, so this parameter estimation is conducted in the very sensitive scale. So as other parameters areas, the estimated region is widely spread around this dotted line, and maybe I have not conducted, but maybe there's no significant meaning about lensing correction. However, if the answer of ALP is really here, the lensing correction is important.
Thank you.
Could you please tell us the future direction of this work?
Future direction.
Yes.
about the ranging effect or the tomographic approaches?
Either is okay.
Okay. So about the ranging correction, maybe it is almost done by just improving the calculation code. However, one of my idea is to do some analytical approach to think about the gravitational ranging effect, especially in the very small scale. And so how can ranging effect changes the shape in the very small scale over L equals to 3,000 or something. Yes, this is just a numerical approach. So I want to show some analytical results.
Oh, okay.
So in principle, the axion can also, have fluctuation due to the inflation dynamics or something.
Yeah.
So in that case, so how to say?
So maybe about anisotropic cosmic birefringence.
Yeah. In that case, what will happen? So the gravitational lens seems to be more important.
Sorry. Please repeat.
So maybe I didn't understand very correctly you are talking about, but yeah, I'm asking that if there is some fluctuation, so how sensitive the fluctuation?
You ask about gravitational ranging effect or just cosmic birefringence?
I mean, cosmic birefringence, if there is fluctuation, then I think
yes, actually this work is totally about isotropic cosmic birefringence. So I haven't thought about that yet. Yeah, but at least there's no reported signal for anisotropic cosmic birefringence. But sorry, it is totally different from what my work now. So I cannot answer the exact thing.
Okay, thank you.
Okay, now time is up. Let's thank the speaker again. So next speaker is Namikawa-san. So last speaker of this session is Toshiya Namikawa, and he's going to tell us about cosmic birefringence tomography with length time polarization signals. So please start.
Hi, I'm Toshiya Namikawa from the Cavities FMU, and today I would like to talk about the possibility of using the polarized Rydberg effect to constrain the cosmic birefringence signal. So let me start. So, where is the pointer? Yes. Okay. I see. Anyway, so shall we start? So already previous talks are introduced, but there is a motivation of the study of the cosmic birefringence because there is some hint of the cosmic birefringence from the Planck and also WF data, as you can see here. But in these measurements, the angular power spectrum, the EV cross power spectrum is usually basically assumed a very simple form, as you can see here. Okay. And however, the EV power spectrum significantly depends on the time evolution of the pseudo-scalar fields at especially reionization and recombination, where the CME polarization are mostly generated. And for example, action-like particles and early dark energy are studied in these papers, and EV power spectrum are significantly different from the constant rotation. And also, we can probe the time evolution of phi using the shape of CAV EV power spectrum without worried about the instrumental miscalibration angle, because the instrumental miscalibration angle just constantly rotate the linear polarization. And we called this technique as a cosmic birefringence tomography, because we can probe the different the information about the cosmic birefringence at different source redshift. And in this talk, I discuss new tomographic sources, the polarized synthetic relativity effect, we usually call PSD, which is sourced by the free electrons at the red time of the universe. So in principle, we can probe the red time of the cosmic birefringence using these signals. So let me first explain the PSD effect. So in order to explain this, I will first explain how the CNV polarization is generated. So basically, the temperature curve anisotropies can generate linear polarization. So if you can see here, from the along the x-axis, the unpolarized photons are coming down and scattered by the electrons, and then the scattered photons go to the along the z-axis. So in this case, the polarization state has only along to the y-axis. So if you combine this unpolarized photon coming from the x-axis and y-axis, but these unpolarized photon has a slightly different temperature compared to the average. The scattered photons contain some linear polarization state. Okay. And for the recombinations, the temperature chlorophore at the recombination produce a linear polarization scattered by the electron at the recombination epoch. And we observe this polarization. And similarly, reionization or after the reionization, there are some electrons. And these electrons can also scatter the CMB photons. And similar to the recombination signals, it produces the linear polarizations. Okay. And this has been already proposed by very previous papers. So PSD can be used to probe the time evolution of the phi in the red time of the universe. If we can measure this QE is a kind of polarization signal. Okay. And so I will explain more details. So what we can observe is Stokes Q and U parameters in observations, and which contains the PSD contributions. And PSD contribution is roughly the local polarizations at the electrons and also the electron number density integrated along the line side. And this is a very simple case. So only there is an E-mode patterns at the electrons, and also the electron number density is basically homogeneous. And in this case, the observed PSD E mode and B mode is given by like this. So there is no B mode contributions. But if the electron number density has fluctuations, the pattern becomes no longer symmetric. This means there is partially some B mode polarization, because E mode is a basically symmetric pattern. So mathematically, the B mode is given by like this, which contains electron number density. And so far, I only consider the local polarization containing only E mode polarizations. But if we consider the conic birefringence, the polarization at the electrons also has B mode polarization due to the conic birefringence. And so, for example, observed B mode contains both the B mode from the electron number density and also the intrinsic cosmic birefringence induced B mode polarization QB. Okay. So if we can extract this QB, we can measure the cosmic birefringence at the red time of the universe. And now I explain how to extract this signal. So again, the PSG is roughly the local EV modes cross some density fluctuation. So basically roughly given by like this. And what we observe in the CMB is in the right side. And but we can also observe the density fluctuation from the galaxy surveys. So using these two informations, we can extract QE and QB by combining galaxy and CMB observation. Okay. So PSC estimator is basically given by the cross correlation between the observed CMB polarizations and density fluctuation obtained from galaxy surveys. And for example, if you write down the estimator, as you can see in the left, QE hat, which is cross-correlated with E-mode observation plus cross-correlated with galaxy over density. This is roughly given by the proportional to the QE. And here I is some redshift information. And similarly, if you use observed B mode, you can also reconstruct the local E mode. And further, you can also reconstruct QB using observed B mode and galaxy over density, but some technically using some different cross-correlation technique. You can get QB. And QB is contains a birefringence signal. So beta I here is a birefringence angle rotation angle. So by measuring this QB, we can constrain the birefringence angle but at red time. So we can realize a tomography measurement of the converging birefringence angle. And so there is a new correlation induced by the cosmic birefringence using E orbs, B orbs, and measured QE and QB. So again, the QB contains the cosmic birefringence signal. So if you, for example, cross-correlate the observed E mode, you will get the equation like this. And also QE, QB cross-correlation also has cosmic birefringence signal. And actually, the previous study considers cosmic birefringence effect on measured TSA signals. However, we should also consider the cosmic birefringence signal in the total observed B modes, because total observed B mode contains the PSC contribution. Right. So if you consider this contribution, there is also additional correlations, as you can see in the right. And we can also use these correlations to constrain the cosmic birefringence angle. So next, I show some result of the angular power spectrum and some noise level of the this measurement, assuming some specific experiments. For example, in the left side, the black solid and black dashed line is a signal from low redshift contributions, and this is a E cross QB. And in the above, there are several lines, and this is a noise from the future CMB observation plus galaxy surveys. And as you can see here, it is very hard to measure these cross correlations. And also in the right side, I show the QE-QB cross correlation. In this case, the noise level becomes still lower, but it's still a bit difficult. By the way, in this case, the signal spectrum assume a 0.34 degree rotations, and also assume some 40% of the sky. So yeah, and so next one is the correlation for new cross spectra, so which was not included in the previous works. And so in this case, the measurement is much more easier than the previous cross spectra. So, for example, QEB is obviously higher signal to noise than the previous cross spectra. And also, EB cross correlation can be also used to constrain the conic birefringence at somehow high redshift. So missing terms have basically better sensitivity to conic birefringence, especially at high redshift. So next I show the expected constraints on the birefringence angle at each redshift beam. And so the dashed line is basically the result from the previous works. And the solid line is including the new terms. And these new terms actually suppress the constraints. And so these terms are basically very important at high redshift. And also, this is a constraints on a fractional change of the expected constraints by using only specific odd party spectra. For example, the dashed line is only using EB spectra. So at high redshift, the fractional changes and there's almost no change. But if you go to low redshift, there is some increase. So this means the EB spectra is mostly does not constrain the low redshift part of the birefringence angle. And on the other hand, the solid line is a cross correlation between B and QE, and this also can also constrain the low redshift part, but not so significant at high redshift part. And also finally, there is a thin thin line which use the QE QB, and in this case, the constraint is very weak. Yeah. So basically, my main message is hidden by this part. So rosy part is basically determined by BQE, and high redshift part is determined by EB spectra. Okay. And let me summarize my talk. So we forecast expected constraints on the birefringence angle with rightward like and also CMBS4 or future galaxy surveys. And we include all relevant terms, which was missed in the previous works. And I found that these missing terms are very important. And also, the functional constraint on the rotation angle at each redshift beam is roughly a degree to degree level. And so currently, I'm not sure what kind of model we can use for this technique, but so PSD would be somehow useful to constrain red time birefringence. I'm not sure about some domain wall or something. Yeah, thanks.
Thank you very much. So is there any question or comments? Oh, yes.
Thank you. Yeah, thank you for your talk. Yeah, just about the final point about domain walls, maybe, or well, just axions in general. Can you use PSD to constrain some properties of dark matter, like axion dark matter? Yeah.
So I think if my understanding is correct, the axion dark matter is more somewhat heavy, so 10 to the minus 20 to EV or so. So in that case, the pseudo scalar field is already decayed, I think, and so it's quite difficult to constrain using this technique, I think. Yeah.
Okay. Any other question or comment? So we are behind the schedule. If not, let's thank speaker again. Okay, so this is over. So this session is over, and the next session will start at 3:20. Okay.
Yes.
Thanks. So okay, so let's start the session. The first speaker is the Alessandro Greco, and so we're gonna talk about the probing axions through tomography of anisotropic cosmic birefringence. So please start.
Okay, so first of all, do you see my screen? Okay. So do you see my screen?
Yes.
Oh, okay. So before to start, let me thank you for this opportunity and apologize for not being there in person. But some problem with my passport and other personal issues. So in any case, I apologize and thank you again for this nice opportunity. So I know that all the people in this audience are really expert in this topic of the Birefringence. So I know that this will be like teaching religion to the cardinals. So I will skip. I will give you an introduction, but of course I know that I'm really a lot of expert here, so I will be really sloppy in that part. Let me say that. Okay, I'm Alessandro Greco, third year PhD student at the University of Padua, and today I'm going to present you the content of my second paper with Nicola Barto and Alessandro Profuso from University of Padua in North Bologna. As Messi mentioned, the title of the talk is about probing axions to tomography of anisotropic cosmic birefringence. So it's a talk about the CMB basically, and how we can use CMB in order to detect part of the dark sector of our universe, because we know that the CMB is nothing but a sort of primordial witness of the early stage of the universe. It's electromagnetic radiation, which is the remnant of this early stage of the universe. And we also know the CMB, of course, you're again really expert in this, is polarized in modes and modes. And we know we can make prediction about what is the source of this polarization and compare theory with position to infer some important physical information. One of the most important things about that is that E modes and B modes, in analogy with electrostatics, are not correlated if no parity violating mechanisms are involved. And so we can use this particular observable in order to test some parity violating extension of the standard paradigm of physics. In particular, this is possible because CMB is a regime in which we can test very extreme regimes of energy and not. So the idea is that as we can study a modification of gravity, we can also study modification of electromagnetism. We know that in the standard Maxwell electromagnetic theory, we have this simple and elegant Lagrangian density. F is, of course, the Maxwell field tensor. But the point is, what if instead we add a modification, a Chern-Simons modification of electromagnetism? Well, the idea is that if we add an extra coupling between a pseudoscalar field chi and the Maxwell dual tensor, then we have an important chronological consequence. What we can see, and I recommend this nicely reviewed by Chico about that, it's just an example. There are a lot of references about that. We have the so-called phenomenon of birefringence. The idea that the linear polarization plane of the electromagnetic waves is rotating because of this new coupling. Notice that this GIF is just a sketch. It's not exactly true because this can be seen that we have some circular polarization. This is not true. We have a rotation of the linear polarization plane, which is a bit different, but I just want to give you a simple and nice sketch. So now we talk about cosmic birefringence because the photons that we are interested in are the CMB photons. That's why we talk about CMB photons. And if we have effectively this modification of the theory of electromagnetism, then we have the rotation rotation of the linear polarization plane of the CMB. And then we have this impact on the EMB modes because we can see a rotation of the Stokes parameters, which is parameterized by the birefringence angle alpha. So alpha is also related to the physics of the pseudoscalar field, which is coupled with the electromagnetic dual tensor. And we can use cosmic birefringence in order to study and investigate the physics of such a field, because as you see, it's related to how much the field value is variated from the photon emission time to the photon observation time. So we can use Casimir Birefringence to test the possible identity, let me say, of this field chi, which could be, for example, early dark energy in the form of the Nambu-Goldstone bond. Exactly today, I say that archive, there is a new paper by Eskil and Komatsu and other people, which there are some new constraints and new studies about how we can constrain early dark energy model with Birefringence. So it's a very hot topic. And also dark matter in the form of ultralight action, which is, for example, something related to the title of this important workshop. So this is a brief sketch, just to be very introductory. The Birefringence mechanism is an interesting phenomenon which we have the photon emitted at last surface, and we observe them today with our telescopes and other experiments. Of course, there is a modification also in the lambda-CDM model, even in lambda-CDM model context, because we have that the Stokes parameters have a modification due to the weak gravitational length. We have a modification of the line of sight to the, let me say, the interaction of photons with the large scale structures. Cosmic Birefringence has an additional modification because we have that Stokes parameters rotate, and so we have a net modification effect. So this is just a simple sketch. This is not philosophy, it's a very physical important investigation, and so we have some constraint, for example, on isotropic Cosmic Birefringence, because if the rotation angle is isotropic in the sky, and so we label it with alpha naught, then we talk about isotropic Birefringence, and there are a lot of important measurements that constrain this effect, because we can use the power spectral lambda, of the CMB observable, and we can compare the lambda CDM predicted model with that affected by Cosmic Birefringence, and that eventually we are able to measure today. Because, as I mentioned, there are some cross-correlating, some cross-correlation that are parity violating. And if Cosmic Birefringence is present, we have a modification that is able to parameterize, we say, this phenomenon, so we can compare them and have an important constraint. These are the recent constraints, just a summing table about Planck and WMAP. There are also other experiments, just to give you an idea about how we are able to do that. And you can see that at the moment, it could seem that alpha naught equal to 0 is excluded at 99% of confidence level. This is really interesting. If the result will be confirmed after a more rigorous analysis of emission galactic, the emission due to the foreground of galactic dust and other possible miscalibration angles and other systematics, well, it could be revolutionary because it will be effectively the proof that this effect exists, and so it will be really everywhere. You have to be really careful about it. So, in reality, I'm talking about anisotropic Birefringence, which is what happens if you include the possibility that the field chi is not homogeneous, but it got some inhomogeneities. Well, the net effect is that we have anisotropies in the angle alpha. This can be easily understood because, of course, we have seen that alpha is related to the variation in value of the field chi, and so if we add inhomogeneities, we have also anisotropies in this angle. So we can decompose this field from the sky, as standard in cosmology, with our old friend spherical harmonics from quantum mechanics, and also about this observable, there are important observational constraints. For example, there is a nice map made by the Ferrara group on Planck in a very nice paper by Marco Bortolano of the last year. And here we can see, for example, a sum of the constraint of the scaling variant angular color spectra between anisotropic Birefringence angle within itself and its cross-correlation with the other standard CMB observable. This is an idea to say that we are not talking about philosophy, but as I said, really physical investigation. So the point is, I know that there are also important people in this audience that are really expert also in tomography of Cosmic Birefringence, but let me just explain the philosophy. The idea is that Cosmic Birefringence is related to how when the photon has been emitted. Of course, we know that CMB photons were mainly emitted at the time of recombination, but technically also at ionization. So Let me give you again the sketch of the previous of my previous statement. We have a photon visibility function that describes the probability the photons will be emitted in a given time, a given relative, and we know that, as I mentioned, the first peak of this visibility function is a recombination. And so we have, of course, a Birefringence effect coming from a recombination. But if we also include the second peak at reionization, when the stars forms, technically we have also to take into account the possibility that there is a second Birefringence effect coming from reionization. So we can use a sort of tomography of cosmic birefringence in order to get information on the axion like this. So we can build a model, okay, and we can try to test the prediction of this. Because, for example, the Lagrangian density in the form of this potential encodes important information, the mass, the coupling, and all the parameters you want to use to define the model. And we can use this tomography approach to test it. So it's like to use Birefringence, because Birefringence is like a sort of time machine. Okay, so this is a very nerd moment, but let me proud of it. So, like having a time machine in which we have our tools, the action evolution and the Birefringence angle, and we use them to disentangle between different models and study cosmic birefringences. So, in this second paper that I mentioned, we have extended this to the anisotropic conservation. So, as already done, I have the people literature, for example, Nakatska, he is a very nice paper. We have solved the equation of motion for the background field, and we have found different solutions according to different times. This is, different solutions according to different mass, where the mass is a parameter that enter in the definition of the potential. Okay, different potential, of course, give different evolution, but this is an example. Okay, we have tested this kind of potential. And also, it leads to different equation of state, and it's really important because it means that we can use the tomographic approach to test different masses, so different kind of definition of the cosmic species of type, because it could behave like dark matter or dark energy or whatever. And so we have extended this to the anisotropic signal. We have included the idea that we can have anisotropic birefringence also from ionization. This is the current state of the art of the definition of the anisotropic birefringence of a given time. We are working to improve this kind of description. And we have solved the equation of motion in Newtonian gauge for the initial condition. So basically, we have implemented anisotropic birefringence in a Boltzmann solver like class. So also the physics of the axion perturbation, and we have studied what happens and with a tomographic approach. So we have computed all the relevant cross spectra and the spectra of this new observable, the anisotropic birefringence coming from recombination or reionization. And then that's what happens. We see that, for example, for this set of parameters, okay, we have that increasing the mass, because if you remember the definition of the mass in the potential, we have an increase also, an enhancement of the amplitude of the anisotropic birefringence spectrum. This is very interesting because it means that you technically you can test a wide range of mass with this kind of approach. And so we have also performed a tomographic analysis. And as I mentioned, we found that larger the axion field mass, again, called the definition of the mass in our potential, larger the spectral amplitudes are. And that for a sufficiently like axion, the reionization signals can be larger than the recombination on large scales. So, for example, these are the alpha E, alpha T, and alpha power spectra for different masses and for recombination reionization according to the dashed or straight line. Okay, and you can see that what I mentioned is exactly true. That for sufficiently light axion, the reionization interval can be larger, so it's important to take into account. So it's also an important impact on the observable, and I'm going to close to finish, because both the components of the cosmic birefringence, the tropic and the topic, and both from both the source, the recombination reionization, contribute to inducing an overall modification of the spectrum. So we have derived a new formula that completely describe this effect, that are sort of generalization of the current formula used in literature. And so we can try to use the tomography approach in order to constrain, for example, a Rydberg energy model by using this kind of expressions. For example, we have simulated CMB power spectrum again by using a Boltzmann code, and you can see what is the modification for different masses with respect to the lambda CDM model, where we have taken into account all the possible effects of cosmic birefringence, isotropic, anisotropic, ionization, recombination, whatever you want. In the case in which we have just scalar perturbation and no length. Of course, the dominant contribution is expected to come from the asymptotic birefringence. So these plots are completely consistent with other that you can find in literature. And these are, for example, the EE spectrum, the BB spectrum, and the ED. And also the cross correlation between polarization and CMB. So let me finish. We have considered a well-motivated particle weighting extension of the magnitude, which induced the phenomenon of birefringence. And so we have computed the angular perspective involved in the isotropic angle alpha 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 T alpha. So we have performed tomography treatment in analogy with what has been done already in literature for the isotropic counterpart, and we have extended it also to the anisotropic counterpart. So we found that our approach is able to make multiple unique features of the birefringence isotopes. For example, the fact that if you enhance the mass, you enhance also the amplitude of the anisotropic spectrum. And also we have found that for low multiples and for sufficiently small values of Axion mass, the ionization contribution is higher to the recombination one to cosmic birefringence. And so, for example, a future development of our research could be trying to use this signal coming from ionization included in anisotropic cosmic birefringence as a probe of the Axion parameters. But not only, we have a lot of ideas in that. So I really thank you for your attention. And if you have a question, you're welcome.
Thank you very much for interesting talk. So, question? Okay, so.
Thank you for interesting talk. So I have a question about the expected constraints on the anisotropic birefringence from the realization. So I think you said so the anisotropic birefringence at the realization is much larger than that produced by recombination. So, but from the observational point of view, so in order to measure such reionization by anisotropic birefringence signal, we have to limit the multiple range of the CMB multiples to only roughly 10 or so. So in that case, the reconstruction noise of the anisotropic birefringence becomes also much larger than the usual case. So do you have any investigation already, or do you have any comments on this? Or?
Well, of course, you're perfectly right. Indeed, we are completely aware that doing this in reality, let me say, would be extremely challenging. Indeed, it's really complicated also to, for example, I mean, compare the current observational constraints on isotropic of the birefringence of recombination, also considering the reionization one. Because, as you mentioned, the problem large scales still remains in any case. This is theory, okay? So, of course, I'm not an expert on the observational side. This is a theoretical work, but you are perfectly right. Let me mention that this is not, let me say, our definitive idea for considering the reionization contribution to recombination. The reionization contribution to cosmic birefringence. We are at the moment working on a project, and we hope that our draft will be released very soon on arXiv, maybe in the next month, in which we are trying to adopt a sort of effective approach, in which we are trying to construct new estimators and new observables that are able to completely, let me say, to completely encode the eventual time evolution on the emission time of the photon of the anisotropic cosmic birefringence with respect to the photon time of emission. Trying to do something that has been done in literature for what concerns the isotropic part. Okay, so let me say that this paper is a sort of a transition paper, which we are for the first time trying to introduce the ionization contribution to an anisotropic cosmic birefringence, but we are still working trying to let me say to provide a theoretical formulation that could be more suitable, okay, for observational. So my answer is we will see. We will see. Okay.
Okay, thanks.
Thank you.
So, any other questions? From people on Zoom? No? Okay, so time is almost over. So if not, so let's thank Alessandro again.
Okay.
Thank you.
Thank you. It's been a pleasure. Thank you again.
Okay, so let's move on to the next talk. The next speaker is Jordan Gaze. Sorry if my pronunciation is not correct. So we're going to talk about the search for vector dark matter in microwave cavities with Rydberg atoms. So
hello, can you hear me?
If we are ready, so yeah, please start.
Like you can hear me?
Yes.
Okay, great. Okay. And do you see the mouse?
Yes. Yes.
Okay.
Perfect.
Very good. Okay. Okay. So hello. First, I would like to thank the organizer to let me the opportunity to give a talk here. So my talk will be centered around an experiment that I've been modeled in the team I'm working on. So in Paris Observatory. So basically, this is a proposition of an experiment to search for a specific dark matter candidate, which is dark photon. So the experiment has not been built yet. So it's just a theoretical modeling of the experiment. Okay. So here I'm starting by showing you the different classes of dark matter that exist. You might have already seen this this picture. So in blue you have the different some kind of dark sector candidates as function of the mass of the given particle. Here, for example, you see the so-called WIMPs. Now, in my talk and the experiment I'm talking about, I'm interested in what is called ultralight dark matter, which are basically particles, dark matter candidates with mass lower than the kilo electron volt. And so you see that the mass the mass range is quite important. And so basically for these smaller mass, you need specific kind of experiments to be able to detect them. And so I will present you one idea of them. And so in the following, I'll be interested in ultra dark matter mass in the micro EV mass range, which I show here in orange. So going further in ultra dark matter. So here I present you the occupation number in phase space of a group of particle as function of the energy density here, the mass and the velocity. Now, if you plug dark matter parameters for the energy density and the velocity, and if you consider mass lower than 10 eV, you can show that this occupation number is greater than 1, which means that the the field in question has to be bosonic by de Pauli exclusion principle. And then if you consider the mass to be much lower than the electron volt, this occupation number gets much greater than 1, which means that the field can be treated entirely classically, and you do not need to quantize it and consider interaction between single particles. Now, you have different dark matter, ultra dark matter candidates. So you can have scalar fields. pseudo-scalar fields, and finally vector fields. And one example of it is called the dark photon, and this is the one I'm interested in this talk. So let's look up about the phenomenology of the dark photon. So basically, cosmologically, you can show that the dark photon field is just a classical field, so it just oscillates at its Compton frequency omega here, which of course, if you consider the field in its own rest frame, corresponds just to the mass of the particle, since the propagation term is zero. And now, if you consider that dark photon is dark matter, and if you consider the galactic velocity in the dark matter halo, which is much lower than the speed of light, you can even make the assumption that in our frame, so in our lab frame, the field will have this form, meaning that we can also neglect the propagation term in our own lab frame. Now let's look at a bit about the dark photon interaction. So here I'm presenting you one interaction of interest, which is with the of the dark photon, which is with the photon field. So through this Lagrangian. So in blue you have the usual electromagnetic sector. In green, you add the dark photon sector with you here, the kinetic term and the mass term. And then you consider a coupling between the photon field and the dark photon field through what is called the kinetic mixing coupling given by this parameter chi. Now, what you can show is that this mixing generates a standard electric field that fills the whole space and which has this form. So you see that this field, this electric field is proportional to, of course, the coupling chi. And you can see that it also oscillates at the same frequency as the dark photon field itself. So basically what you have is just a very small electric field with very small amplitude, just standing and oscillating at the Compton frequency of the dark photon field. And of course, this is the electric field we'd like to detect, or at least build an experiment that is sensitive enough to this field to be able to constrain the coupling chi on a given range of dark photon masses. And of course, if you consider the dark photon field accounts for the whole dark matter, you have another information on the amplitude of this field, and which is related to the dark matter local energy density. Okay, so now why using a resonant cavity in this context? So consider this small electric field oscillating anywhere in space, as I told you, and now consider also a perfect metallic plate anywhere in space. What you will have is something like this. So you have the background standing field in yellow here, and of course, by boundary condition at the edge of the metallic plate, you need to have the total electric field. I mean, the parallel component of the total electric field at the edge of the plate has to be zero, and to do so, basically the plate will emit a standard electromagnetic field that I call EDP parallel, with the same frequency as the background field in yellow here, and with the amplitude which corresponds to the projection of the background field to the parallel of the plate. And so basically now, if you consider a one-dimensional microwave cavity where you have two non-ideal mirrors facing each other, of course, in the same way as in this kind of cavity, if you plug inside an electromagnetic wave, if this electromagnetic wave has the right frequency, you can enter in resonance and you can enhance a lot the amplitude of this field. So which means that this instrument is the ideal instrument to enhance this weak dark photon electric field. But of course, since you have non-ideal mirrors, you have a loss of energy, which is characterized by the mirror's reflectivity R, which is related to another parameter of the cavity, which is called the quality factor. Okay, so now let's look at the experiment. So from what I said, you could think, okay, let's just consider a microwave cavity and let's try to detect this small electric field. So in this case, if you compute the total electric field inside the cavity, we'll have something like this. So XDM is the amplitude which is proportional to the coupling chi. And then of course, you have a frequency which is unknown that I call omega dm. Now, the problem with this thing is that basically the amplitude proportional to chi is way too small to be enhanced by any kind of cavity. So which will make the detection a bit complicated. And also, as I told you, I'm interested in dark photon masses around the micro EV mass range. And so this corresponds to gigahertz frequency range. And which means that the oscillation is a bit too fast to have a good accuracy on the amplitude during the detection. So what you can do instead is apply an external field that I call EA with amplitude XA and frequency omega A, and try to measure the square of the total electric field. So here I show you an update of the little scheme, of the little previous scheme. So you still have the background field in yellow. You still have the contribution to the dark matter field in orange inside the cavity. Now what you do is just apply another another electromagnetic signal in the cavity, and by the same boundary conditions as the dark photon field, of course, you will have a propagating contribution inside the cavity that I show in blue, of course, with different frequency and different amplitude. Now, if you compute the total electric field inside the cavity, you have something like this. So in gray, you still have terms which either oscillate too fast or have too small amplitude to be detected. But you have one cross term, which I show here in green, which oscillates at the difference of frequency between the two contributions inside the cavity. So omega A minus omega dark matter, that I call delta omega. And of course, this can be small, and this can be detected if this difference of frequency is lower than the sampling frequency of the apparatus. So here, this condition. And also, you see that the amplitude, of course, is proportional to XDM, so to the coupling chi, but it's also proportional to XA. So what this means is that you can also use the applied field to amplify even more the weak dark matter field to be able to detect it more easily. Okay, so now we have an observable to try to detect this small electric field, but how to measure it? So we think that the best way of measuring the square of the total electric field is through what is called the quadratic Stark effect, which basically links the transition frequency shift of atoms delta nu to an electric field that is applied to them through what is called the polarizability of atoms, which is here delta alpha. And so basically what you can do is just put some atoms at the center of your cavity and try to measure the transition frequency of them and look for time oscillation in the signal, and of course, oscillation at frequency delta omega. So let's update again the previous scheme. So here I just add some atoms at the center of the cavity. Now you see that I'm considering not regular atoms, but Rydberg atoms. So Rydberg atoms are special atoms with a high principal quantum number n, and which means that basically the electrons are much less bounded to the nucleus as regular atoms. And so, of course, this means that they are much more sensitive to an application of an electric field. So if they have a lot of different advantages, one of them is that they have a large polarizability delta alpha. So of course, if you come back to this equation here, a small electric field will translate into a high frequency shift, and of course, more easily detectable. And so also you can show that this polarizability delta alpha is proportional to n to the 7th power. And so of course, if you if you increase the quantum number n, of course you will increase the polarizability. They have also some other advantages. One of them is that they have a short lifetime, so of the order of microsecond, and they also can be used in what is called non-destructive measurements, which basically means that a single atom can be used for multiple measurements of the electric field. And so what this means experimentally is that we can use a higher sampling frequency as usual, which is also interesting for the sensitivity. So now let's look at the estimation of the experiment sensitivity. So first, I need to introduce the different sources of noise that can limit the sensitivity of the experiment. The first one is a statistical noise and is related to the measurement uncertainty and the frequency shift of atoms. So basically what this means is that you have a non-zero variance on the frequency shift delta nu, which is related to the noise power spectral density and the sampling frequency, and this will imply this will induce a measurement uncertainty on the electric field squared, just following the Stark effect equation, where here SC squared is just the electric field square noise PSD. So basically a non-zero variance here will induce a non-zero noise PSD here. And so we for the experiment, we've considered Rydberg atoms with n greater than 60, which means that we can reach these experimental numbers that I will not talk more here. Okay, now a second source of noise is a systematic noise, and is related to the amplitude fluctuation of the applied field, which is characterized by what is called the relative intensity noise, or RIN, of the signal generator. So basically what this means is that instead of having a constant amplitude XA, you're more likely to have a stochastic expression like this, where basically you have a fluctuation delta XA over XA of the amplitude, which oscillates at frequency omega naught, and whose amplitude also depends on omega naught. Now, this quantity here, delta XA over XA, is directly related to the relative intensity noise power spectral density that I call SRIN. Now, if you assume a flicker noise, which means a noise which is inversely proportional to the frequency, you can show that the main amplitude fluctuation, which means a noise which mimics a signal oscillating at delta omega, is exactly at frequency omega naught equal delta omega. So this means that you can just simplify this complicated expression to this one. And so it just means that you've just considered the fluctuation which occurs at omega naught equal delta omega. And so, of course, this means that you still have another noise term that you need to take into account in your modeling. Okay, so let's go. Let's see the experiment sensitivity now. So here I present you the current search for dark photons through their kinetic mixing coupling chi with photons here in the y-axis as function of the dark photon mass on the x-axis. So you see that this parameter space is already well constrained. In blue, you have some constraint from cosmological observations. So for example, from the CMB. In green, you have constraints from astrophysical observation. And in red, you have a constraint from lab experiments. Now, if you zoom into this part, you get this. So here are the different already existing experiments trying to hunt dark photon. And so the experiment I'm presenting you today would have the following sensitivity here in orange. So you see that here you see at some points here the peaks, the sensitivity peaks are related to the cavity odd modes, where you have, of course, more sensitivity than elsewhere. And so what is interesting is that you see that at some regions of this parameter space, this experiment could enable to scan regions that have never been scanned before, which is, I think, quite interesting. And so just to give you some order of magnitude, if experimentalists wanted to, for example, scan the region between the two light blue lines here that I show here, they will need approximately 5 days of data taking, which, in my opinion, is a reasonable amount of time for an experiment. So now I arrive to my conclusion. So I think the home tech messages are that dark photon is a serious dark matter candidate, and that numerous lab experiments are trying to detect it. Here I propose you a new kind of experiment which is looking for dark photon using atoms inside the microwave cavity. And what I've shown you is that with the current technology in atomic physics, we obtain a competitive sensitivity on the coupling constant chi compared to other already existing experiments. And also we think that the experiment could be feasible in the near future in labs, for example, using strontium or mercury atomic clocks. So I thank you for your attention.
Any question?
Thank you for the talk. I guess you will need some electric field or magnetic field to trap the atoms.
Mm-hmm.
Do you expect any noise from that kind of trapping fields?
No, we've not modeled this kind of node because we think that this should be I mean less this should have a smaller contribution than the noises I mentioned. But of course, in a more realistic experiments, so here it's just a theoretical modeling. But if at some point the experiment is run, of course we have to we need a much more precise modeling, and of course then consider all the different even small sources of noise that could limit the sensitivity, but
Okay,
which we didn't hear.
Thank you.
Thank you.
Thanks for your talk. Can I ask you what drive your choice of the frequency of cavities?
So basically, you mean why microwave cavity and, for example, not optical one?
Yeah, and also the which how you design your cavity, which frequency you want to design the cavity for?
How we design?
Mm-hmm,
right?
Yeah.
Okay, so for the first part, so why microwave and not optical, for example? So the problem with I mean the problem. Let's say that in microwave cavities, it means that you are looking for fields with lower mass than in optical range, and so as I said in the beginning, it means that you can just model your field classically, which is of course easier than that quantize it. And so of course in the optical range, like the mass is closer to the EV, and so you would need a bit of quantum field theory, which is a bit, I mean, which adds a bit of complexity in the modeling. And also, as I said in the very beginning, we're considering that the propagation of the field is neglected. So basically, we just have even in our lab frame, we just have a field that a standing field that doesn't propagate. And so this for the size of the cavity that we're considering, so around 10 centimeters, this is valid only in the microwave regime and not in the optical one. Like in the optical one, basically we would not be able to neglect this propagation term. And so of course this also complexified the modeling. So I don't know if this was your question or not.
Yeah, thanks. Yeah, that answers my questions. Thanks.
Okay, thank you.
So any questions or from audience in Zoom? No? So if not, so let's thank Jod again. Thank you very much.
Thank you very much too.
Okay, so let's move to the next speaker. The last speaker of this session is Marta Monelli from MPA. It's going to talk about the impact of half-wave braid systematics on the measurement of cosmic birefringence from CMB polarization. So when you're ready, so please start.
Yeah. Can you hear me well and see my screen?
Yes.
Okay. So yeah, thank you for allowing me to present and for introducing me. I am going to talk about some work that I've been doing together with my supervisor Eiichiro Komatsu and a few other collaborators to try and understand how systematics can affect cosmic birefringence measurement. So to give a super quick introduction, we know that the CMB is characterized by having anisotropy in both its temperature and polarizations. And these are believed to be sourced by primordial perturbations coming from inflationary stages. And the primordial perturbation can be classified into scalar and tensor modes. And while the scalar modes can only produce temperature anisotropies and E modes, tensors can also produce primordial B modes. So a detection of those would help constraining inflationary theories and have proof that the inflationary scenario we have in mind is working. This is driving a huge experimental effort. Many new generation CMB experiments are exactly aiming to constrain or measure these primordial B modes. Among them, we have Rydberg, which is the one that I'm focusing on, which is going to be a spaceborne mission that aims to measure R, so the tensor to scalar ratio, or constrain it up to around 10 to the minus 3 on very, very large scales. If we take a look at this plot, we already see how ambitious this measurement is. If we compare the black dots with error bars here and here, which is the forecast of Rydberg sensitivity, if we compare this to what was measured in the past, we see how the error bars are very tiny, and also nothing was measured in this region before that. So we need to have incredibly high sensitivity in order to make this measurement. And we need to be extremely good at measuring polarization in order to constrain B modes. So people are thinking that, okay, if we are so good at measuring polarization, we might also be able to measure cosmic birefringence, which I'm sure everybody knows what that is in this audience. And also Alessandro before did a nice recap about it. If there is a time-dependent party-violating pseudoscalar field filling the universe, then the plane of linear polarization of photons is rotating while they propagate through the pseudoscalar field, and the total rotation from CMB, the decoupling time to today, amounts to this cosmic birefringence angle beta. The cosmic birefringence angle then mixes E and B modes, because if we started with a perfect E mode, in the end we have some E and some B, and we can see this in terms of the spherical harmonic coefficients here. Writing down the angular power spectra, these are the relations. And one can use the fact that there is this identity among all the observed quantities to try and infer something about beta. This is a bit complicated because there are also other systematics that can enter in this sense, for instance, the miscalibration of polarization angle. But it was possible for the first time in 2020 by Minami and Komatsu. They managed to constrain beta anyway, using the fact that foregrounds and CMB are affected differently in this way by the miscalibration and cosmic birefringence. So there is, one would want to make this measurement without having to rely on foregrounds. So again, we need to have a very, very good control over systematics, because in this sense, the miscalibration of the polarization angle should be taken into account in some other ways if we don't want to use foregrounds. One method one strategy that has been proposed to account for the systematics and to have better polarization measurement is to use an half-wave plate as a polarization modulator. So an half-wave plate is an optical element that is characterized by having a fast and an orthogonal slow axis. When light that is polarized along the fast axis travels through the half-wave plate, through the material, it does so slightly faster than the component that is polarized along the slow axis. And this causes is exactly as like a birefringence material, and this causes the incoming and outgoing polarization vector to be different. And in particular, one is the image of the other under a reflection with respect to the fast axis, essentially. If this half-wave plate, this optical element, is rotating as a first optical, like a first thing that photons encounter going in the telescope, essentially, then what happens is that the signal, the polarized signal, is modulated to 4 times the rotation frequency of the half-wave plate. So it's modulated to quite high frequencies, depending on how fast the half-wave plate rotates. And this allows to avoid the region where the 1/f noise is important. So in this way, we escape 1/f noise, which is a systematic that we like to not have to deal with. Another advantage is that allows a single detector to make polarization measurement. Usually you have 2 detectors orthogonal one to the other, but then if the specifics of them are slightly different, it can happen that one interprets as polarization something that is actually unpolarized. So this is again something extremely useful to have good polarization measurements. However, this picture is very, very simplified and idealized, and in reality things are a bit more complicated. To quantify what this means, we can use Mueller calculus, in which the polarized radiation is described by a Stokes vector with I intensity Q and U linear polarization and V circular polarization, and the effect of any polarization altering device is parameterized by a matrix, which is a Mueller matrix, so that the outgoing Stokes vector is given by the scalar product of M and S. For the ideal half-wave plate, so the perfect half-wave plate we can have in mind, the Mueller matrix is a diagonal, and on the diagonal there are 1, 1, -1, -1. In a realistic case, though, things are a bit more complicated. This is the Mueller matrix elements from Giardiello et al., this paper from 2022, where they use a model for one of Lightbird's half-wave plates. So it's a realistic version of what Lightbird half-wave plate are gonna look like. And we see in black is the value of the ideal case, and then the red line is actually what comes up from the model. We see that we don't have just numbers, we have plots, and this is because the response of the half-wave plate depends on frequency. These are the frequency from the medium frequency telescope of Lightbird. And there are quite big deviations here and there. So the question is, how does this affect the observed maps? Because we are introducing the half-wave plate to avoid systematics, but these other non-idealities may cause like secondary systematics in some sense. To try and answer this question, or at least gain some intuition about it, we first worked on a simulation pipeline for a Lightbird-like mission in order to simulate the maps that would be observed with a non-ideal half-wave plate. And we also derived some analytical formulae that were helpful to interpret the output and have some intuition about it. So for the simulations, we should first think about what we should simulate in this case. So in a realistic CMB experiment, what you have is some signal in the sky given by CMB for grounds and whatnot. And from this, we want to make a measurement and extract CMB sky maps. To get there, there are 3 macro steps, really macro steps, super simplifying. One is to proceed with the detection. So you build up your instrument, you put it wherever you want to observe from, and then you start detecting. Ending up with the time order data, TOD, which is a collection of all the signal detected by all the detectors during the whole mission. These numbers here are the reference for Lightbird, so around 4,000 detectors, and the mission is supposed to be 3 years. Taking into account that, let's say, they take 19 measurements per second. So this is a very, very big number of signals, like a very big data array. Once you have the time ordered data, you can proceed with the map making step to get maps for each of the frequency channel of the instrument, and then use the fact that foreground and CMB behave differently, have a different frequency dependence to disentangle one from the other. What we worked on was to work on this TOD step. So to try and simulate how the instrument take data, and in particular, how the halfway plate affect this data. The simulation we worked on builds up the TOD starting from 3 different ingredients, let's say. So the first one is the noiseless TOD. What would the instrument observe in absence of noise? Then the noise, which can be computed separately, and also the dipole signal can be computed separately. For the noiseless part, we make use of beamconv, which is a convolution code that allow to take into account realistic polarized beams together with realistic scanning strategies and together with realistic halfway plate. This is not trivial because the mathematics to implement all of this is quite complicated. And when we started this work, beamconv was the only one that was able to deal with realistic beams and realistic halfway plate altogether. And for the noise part, instead, we used one functionality of DAC. So we have all this pipeline in place to study quite realistic scenarios. But however, for the purpose of the project, since we were mostly interested to see the effect of halfway plate non-idealities, we considered a simplified problem without having the most realistic machinery in place. So we didn't account for noise. There's no noise in the simulations. We consider a single frequency, which is a very, very big assumption, so a very big approximation. We don't include foregrounds, also because with a single frequency, it wouldn't make sense to include foregrounds. The beams are assumed to be Gaussian and axisymmetric, so super simple. And we do not take into account that the halfway plate can be tilted with respect to the detector line of sight. So essentially, even though it's possible to feed the pipeline with whatever input map one wants to do, what we did was just taking the best fit 2018 Planck power spectra for IQ/NU, so for temperature and polarization, and produce IQ/NU CMB maps to feed as an input. For the scanning strategy, one can use many other scanning strategies, but what we did was to simulate 1 year of Rydberg-like scanning strategy. As for the focal plane, we read all the information directly from the Rydberg's database, so this instrument model database, IMO, that contains all the information about the position of the detector on the focal plane, the orientation of the polarization sensitivity directions, and so on. And we consider 160 detectors from one particular channel given from the taken from the IMO. And as for the halfway plate specifics, we actually run 2 different simulations. One where the halfway plate is assumed to be ideal, and the other one where the halfway plate has non-idealities. And in particular, we consider the non-idealities that I was showing before. So we run the simulation like these 2 simulations, one ideal, one non-ideal one. And both TODs, both data sets are processed through an ideal map maker. And the expectation is for the ideal TOD, when I process it through an ideal map maker, I'm putting the same information in the TOD and in the map maker. So I expect to recover the output to recover the input. While for the non-ideal TOD, since the map maker is ignorant about the specifics of the TOD, essentially, there might be some discrepancies. So we run the 2 simulations, we compare the angular power spectrum. Here we can look at this darker gray line, which is the output of the ideal simulation, and compare it with the orange. We see that for TT, there is some leakage, although quite small. But for EE, it becomes much bigger. BB is much larger in the non-ideal case than in the ideal one. And if we go back and forth from BB to EE, we see that he has the same shape essentially. For TE, we again have some small leakage. EB is huge compared to what it was that was compatible with 0, and the same TB. And by looking at all of them all together, we see that there is some kind, we can expect we can interpret this as some kind of leakage from temperature to polarization, which we can see here and also here, and then a strong leakage from E to B. How can we quantify? There is any way to predict what we are observing? We managed to do something in this sense by considering a different parameterization and modeling of the TOD of the data. So what BeamCon does, or any other convolution code does, is to compute the TOD, so the detected signal at the time sample t, as these products, set of products between the beam ALM coefficients and the sky ALM coefficients. However, when the beam is simple, if it's Gaussian and axisymmetric, one can also use a different parameterization, which is what we started from in the paper. So basically write down the measured data, the measured signal, as this matrix product. And it's really simple to understand what's going on. We have some incoming Stokes vector, which is rotated by a psi plus phi, which means that we are going from sky coordinates, where the Stokes vector is defined, to telescope coordinates, and then to alpha plate coordinates, where then we can apply the alpha plate Miller matrix. And then we need another rotation to go in detector in the coordinate of the detector, and finally apply the Miller matrix of the detector and take the first element of the vector. So by doing this, it's possible to write down the TOD, to model the TOD in a very, very simple way. And in particular, it's also possible to model the map. How we got to the map was by starting with a minimal TOD given by only the signal measured by 4 detectors modeled in this way, and then applying map maker to this very, very small TOD, only to these 4 numbers. And what one gets by doing this analytically is this kind of expressions for the estimated output IQ and U, where we see a bunch of terms that depend on sine or cosine of alpha, where alpha is the sum of the halfway plate angle plus the telescope angle. What happens in reality is that you have not just for measurement of the signal in a pixel, but you have many, many of them during the whole experiment. And what having many of these measurement does is basically averaging over this kind of alpha. So if you have a good sample of alpha, which comes from having good coverage and a rapidly spinning alpha plate, then all these sine and cosine average out, and we are left with this expression for the estimated output Stokes vector. This expression can be expanded in spherical harmonic, and one ends up with the CLs, expected CLs. And we see that there is like a big similarity with that and cosmic birefringence, which we will get to. So we want to check if the formula we found makes sense. And to do that, we plot them on top of the non-ideal angular power spectra that I was showing you before. And as you can see, there's really no darker orange in this plot. They perfectly overlap. So we managed to have some analytical formula that recover the output of the complete simulation, at least in this very simplified scenario, of course. As I was saying before, there is some similarity with cosmic birefringence. In fact, the analytic CLs satisfy the same relations as the cosmic birefringence does. In this sense, the alpha plate induces an additional miscalibration, which is degenerate with cosmic birefringence and the polarization angle miscalibration. And from the formula, we can estimate theta hat, so the halfway plate induced miscalibration, which for the single frequency case we consider is around 3.8 degrees. Now, the fact that this is big shouldn't alarm anyone too much, because it's just a single frequency case. It's very simplistic situation, so it doesn't give a realistic idea of how things will look like. And also, regardless of the value, the halfway plate won't necessarily keep us from measuring beta, but this result shows how important it is to carefully calibrate the Mueller matrix elements and to take them into account in the analysis, because the fact that we have this large miscalibration is because we didn't account for it in the map making step. So we played a bit around then with some generalization, so trying to relax some of the assumptions we made. For instance, what happens if we allow to have multiple frequencies, a complete frequency range and not just single frequency? We have that our model for the data changes slightly. We have this integral over the frequency of the Mueller matrix elements multiplied by the Stokes, incoming Stokes vector, which also depends on frequency. And in this sense, what changes is that theta hat is still the same functional form, but now the argument of the arctangent is an average over frequency, essentially. And another thing that we allowed to, we generalized, is the presence of additional miscalibrations that again enter as a contribute to theta hat delta theta, given by the miscalibration of the detector angle minus the miscalibration of the sky, the telescope angle, minus twice the miscalibration of the halfway plate. And there are even more generalization which can be explored, still keeping the analytic character of this formula, this treatment. For instance, one can allow for the bandpass to have a more realistic shape, and also one can allow for the miscalibrations psi and delta phi to depend on frequency. So what we are trying to do now that this first project is wrapped up is to try and push a bit the analytical formula to see if we can exploit them for more realistic scenarios. And one thing that I'm currently working on is try and understand how the halfway plate affects the CLs in a bit of a more realistic way. So including frequency dependence and noticing that while even if without halfway plate one had an experiment that only the output maps were given by the input map of each component multiplied by a factor, a gain factor. What happens with the halfway plate is that you don't have a simple gain factor, but you have this kind of matrix if we trust our simple model. So we have a gain, yes, but we also have polarization efficiency term and a cross polarization leakage. And these are given by expression of this kind. This makes things a bit more complicated because all these effects are frequency dependent, meaning that they affect each component slightly different. And we see here, for instance, I'm plotting the spectral dependence of the CMB, which is like the deviation of the CMB, which is a modified black body, together with a dust reference spectra and a synchrotron reference spectra, and we see that they are affected different by each of these gain and polarization efficiency and cross polarization terms. And this also would mean that if we don't know how to account for the Mueller matrix elements of the halfway plate very precisely, then one can have complications in the component separation step, because we cannot trust anymore the spectra we knew where the CMB dust and synchrotron one, for instance. So to sum up, we have the simulation pipeline that we are planning to adapt to study a bit more complex problems, so to deal including noise, including more realistic beams and so on. There's still a lot of potential there. And then we also have the analytical formulae, which are an alternative to study the same problem more effectively, but with more approximations, of course. And an obvious application, which is what I'm trying to work on now, is to use the analytical formulae to derive some calibration requirement for the halfway plate in order for it not to spoil beam of detection, so not to induce a too large bias on the cosmic to scalar ratio, but also not to spoil a detection of potential detection of cosmic birefringence or the foreground cleaning procedure. Yeah, I hope I have updates very soon, but for now everything is a bit a work in progress.
Sorry, yeah, mic was muted. So thank you very much for very nice talk. So the question time. So any question? Okay, so I have a naive question. So I may miss your point, but so let's see. So to calibrate the non-ideal effect of the halfway plate, so is it possible to use something like a astrophysical sources, so which provides a kind of an idealistic polarization like a tau A or something like bright source? And is it possible to make use of this calibrating source and to, so get rid of more or less the uncertainty of the halfway plate effect? So
okay, this is something that needs to be discussed within the Rydberg collaboration, and there is some like conversation going on about it, because it's like, while for temperature we have the dipole, which is very well known and everybody knows how to behave, so it's very good to calibrate for the temperature. In this case, it would help to calibrate for this term here. But for polarized sources is not that clear. Like, the measurement that we have are not that precise, and people are working on it to try and see if it's possible to perform in-flight calibration, because the problem is that one can calibrate in the lab, which is of course helpful, but then, as you're saying, it would be extremely nice to have an in-flight calibration also. But for now, there are no definite strategies in place for that. So it's something like a really relevant point, and it's something that we should for sure think about. This is particularly important for Rydberg, because for ground-based experiments, it's still possible to, once the instrument is built up, one can still calibrate. Making use of drones, for instance, was proposed, and people are thinking about that. But of course, for Rydberg, it's a bit more complicated to send a drone to calibrate. So astrophysical sources are, of course, something that should be discussed and taken into considerations for sure.
I see. Thank you very much.
Thank you.
So, other question? Okay, so please.
So I have a quick question. So you focus on the angular power spectrum, but is it also produce some non-Gaussian statistics? Or?
I didn't think about that, to be honest. I should think about it before answering. I have never thought about it. It's essentially, I don't know if we can work it out together, because let's see. It shouldn't change the statistical properties of the field, I would say, but I'm not 100% sure. Because essentially it's just a rotation.
Yeah, so basically constant mirror matrix is basically constant in time, and also yeah, so So you only include the scan strategy for Rydberg and probably not, does not produce significant non-Gaussian effect.
Yeah, I would say so, but I should think about it to be 100% sure. But yeah, for sure it's constant in time. I mean, unless the alpha plate breaks at some point, then it should be constant in time. The Miller matrix, I mean.
Okay, thanks.
So, other questions? Okay, so I have another question on the frequency dependence of the half-wave plate. So, is there any, okay, so yeah, the frequency dependence on the response on the half-wave plate looks very random, but is there any primal noise or primal non-idealistic sources which make such a random frequency dependence on the half-wave plate?
What makes things look a bit weird is, sorry, I have to go back a bit. Is that if you only have one half-wave plate, so this simple description that I was talking about, then you can achieve a very good, like a quite good, it can be ideal, let's say, but it's only ideal for a small frequency range. And what people want to do in like CMB experiment is to have broader frequency ranges because we want to explore them to do the foreground cleaning. So when you increase the frequency range that the alpha plate can transmit light, like it's transparent, then you are trading this for more fluctuations and non-idealities. So there is some tweaking that can be done, like if you change slightly how you're building the alpha plate essentially, but there are gonna be always some deviations because it's impossible to achieve a large frequency range, so a quite large bandpass without trading it off with non-idealities essentially. So maybe in the end it's not gonna look like this, it's gonna be slightly better, but I don't expect, like it's never gonna be exactly 1 for the whole frequency range and exactly 0 for the whole frequency range. So these black lines are impossible to recover with the technology we have right now.
So I am not so familiar with the kind of a technological progress on the half-wave plate, but okay, so what is the kind of a best idealistic? Is there any half-wave plate which is the kind of a best kind of a frequency independent responses in the world? So
I assume it's what, like for Lightbird frequency range, it's what people are trying to develop. So we will have an half-wave plate from medium and high frequency telescope and another half-wave plate to low frequency telescope. So even just that tells you how complicated it is. It was impossible to build just one that was with a broad enough frequency coverage to allow for all Lightbird channel to be in the frequency band. So they're developing 2 different ones, and given the different frequency range, they're using 2 different techniques to build them. One is a stack of a bunch of alpha plates, all with different orientated differently, and this allows to have the broader band. And the other one is a metal mesh technology. So there is a lot of effort to try and make these elements as ideal as possible, but it's never gonna be perfect. It's really we need to expect that there are gonna be non-idealities, which is unavoidable, and what we can do is really to think about how to correctly include them into the analysis, in my opinion.
Okay.
Yeah.
Thanks.
Thank you.
So if there's another question or comment, or people in Zoom. Okay, so if not, so yeah, let's thank Marta again. And let's thank all of the speakers of this session. So thank you very much.
Thank you.
Okay, so we have time to coffee break. The first speaker of this session, the Konstantin Springmann. So we're going to talk about how Axions change thoughts. So okay, so if you are ready, so could you share your screen, and then so please start whenever you are ready.
Yes. So hi everyone. Let me try to share my slides. Okay, can you see my slides?
Yes. Yes.
Okay, perfect. So yeah, hi everyone. First of all, thank you very much to the organizers for the opportunity to speak here at this very nice workshop. And today I'm going to talk about how Axions change stars, which is work in collaboration with Reuven Balken from the Technion, Javi Serra from Madrid, Stefan Stelz, who is now in Lausanne, and Andreas Weiler from Munich. And okay, so no, okay, perfect. My talk is kind of split into two parts. First of which is about a project that we uploaded to the archive a couple of months ago, which is how white dwarfs can act as a probe of light QCD axions. So I'm going to have a look at axions at the properties at finite densities, look at kind of a toy model of a free Fermi gas of neutrons coupled to the axions, and eventually talk about white dwarfs and light QCD axions. And then part two is about a project that is still in progress, but will hopefully appear in the archive soon, which is a mechanism to get heavy neutron stars from light scalars. And I will kind of explain how that works. Okay, so let me start with the first part, axions and the properties at finite density. So, okay, the QCD axion is kind of motivated by the strong CP problem, which is kind of the question of why the strong sector preserves CP symmetry. So in principle, you have two sources of CP violation in the strong sector. One is a phase in a quark mass matrix, and the other one is proportional to the GG tilde term, this topological term that arises in QCD. And so in principle, the two sources are not independent, but there's a combination of the two that you cannot get rid of, which is called theta bar. And if this theta bar parameter is non-zero, this predicts an electric dipole moment for the neutron shown here diagrammatically. And we can measure this electric dipole moment of the neutron to very high accuracy, as you can see here as a function over the years. We've really determined this this parameter to very high accuracy, and it's linear in the theta bar parameter. So this really gives a very tight bound on the theta bar parameter. And then from an EFT point of view, one can ask the question, okay, why is this parameter so small? There's a priori no reason why this parameter should be so small. And this is where the QCD axion comes in. So we can add an axial global symmetry, the U1 Peccei-Quinn symmetry, that is spontaneously broken at a large scale that I call F, and also explicitly broken by the QCD anomaly at the quantum level. And okay, if you have a symmetry that is spontaneously and explicitly broken, there is a pseudo-number Goldstone boson that is called the axion that couples exactly like GG tilde. And we can absorb the effective theta bar parameter into the axion field. And the axion will eventually relax at a CP conserving minimum at 0, below the QCD scale. So at low energies, non-perturbative effects generate a potential for the QCD axion that kind of has this periodic shape, which is proportional to a cosine, and the QCD scale here proportional to the pion mass squared and the pion decay constant squared times this periodic function. And so the QCD axion is very predictive. It has couplings to nucleons, to photons, but also electrons, and kind of all of which is determined by the Petchy-Quinn symmetry breaking scale F. Okay, so there's a plethora of experimental searches going on at the moment that look for the axion. So here on the left, I'm showing the coupling of the axion to photons as a function of the mass, and you can see we have experiments like CARS at CERN that look for the axion, but there are all kinds of other constraints coming from astrophysics, assuming that the axion is a dark matter, but also bounds that don't assume that the axion is dark matter. And here on the right, I'm showing kind of constraints on the QCD axion band, which is on the left here shown as this yellow band. And yeah, so here are projected bounds on this line. And so there's a lot of experimental efforts going on to bound this parameter space. And we can also look at the different plane, which is kind of 1 over the decay constant of the axion as a function of the mass. And also here you can see that there are bounds from supernova, from experimental searches, astrophysics, and so on. And so I want you to show that kind of there's an interesting region, which is this upper triangle here, which corresponds not to QCD axions, which are confined on this line here, but kind of extends in this region where most of the searches are going on, kind of. So there's a question, okay, what kind of models lie in this range? And these kind of models are usually called light QCD axions or lighter than expected QCD axions. So before we had basically that the potential or the mass of the axion is fixed by the QCD scale, but there are symmetry-based realizations. For example, the most prominent example of this is from Anson Hook and Yunwoo Huang, who can give you a model that kind of scales down the potential and thereby also the mass, and allows you to populate this part of the parameter space. So here again, I'm showing the decay constant as a function of the axion mass. And so all these light QCD axions kind of lie in this interesting upper triangle of the parameter space that experiments probe and will probe in the future. So these light QCD axions similar or couple in the same way as QCD axions to nucleons. Namely, in nuclear carrier perturbation theory, with the axion or the QCD axion, we can write down this term here, which is proportional to the trace of the quark mass matrix times an exponential which contains the axion times the nucleon, so the nucleon field n bar n. And so this coupling leads, this gives rise to kind of a shift symmetry breaking on non-derivative coupling to nucleons, which we can effectively parameterize as a field-dependent nucleon mass. So this term from carrier perturbation theory gives rise to an axion-dependent nucleon mass that is such that when the axion sits at 0, so in its CP conserving minimum, this gives exactly the nucleon mass and is proportional, but the coupling is proportional to the nuclear sigma term that is very well determined from nuclear physics to be of the order of 50 MeV. Okay, but now what happens if we take these light QCD axions and take them to a finite density background? So that means we are considering now a background density n, which is just giving a vacuum expectation value to n bar n. And then we can see that the axion potential gets, or the amplitude of the axion potential gets corrected by exactly this factor here, which is, so the first term is what we had before, was just the vacuum axion potential, but now we get a correction that is proportional to the number density times the coupling of the QCD, of the light QCD axion. And so if we stay below densities that are smaller than this critical density here, then the axion will still be minimized at 0. But once we exceed the density, so these critical densities, the whole potential of light QCD axions flips sign, and new minima appear at pi times the decay constant. And if we imagine now some kind of object like a star, a neutron star, for example, or a white dwarf, exciting new effects can appear because the axion field will develop a non-trivial field profile that interpolates between the in-density minimum and the minimum in vacuum, which is 0. And this has partially been studied by Anson Hook and also by a paper by us from 2020. And if you consider now, for example, a neutron star or such an axion profile in a neutron star, you can have very interesting effects, which is you can have, if the axion profile extends outside the star, you can have long range forces between neutron stars. You can have axion conversion into photons in the magnetosphere. But there's also this kind of axion phase inside the neutron star, which you can see here, that kind of leads to a back reaction on the system. And this will be the focus on this talk. Okay, so the first question that you might ask, okay, if I just need some kind of density, why does this not affect large nuclei that we have here on Earth? I mean, we know the mass of the nucleon, so it cannot be different. So it is true that we gain energy at large densities once we sit in this new minimum here at pi f. But in field theory, there's also energy contained in a gradient term that appears here in the potential, like so. And this just means that you have to pay a price to go from 0 to pi. And this is kind of similar to saying the field resists a change of profile, or as you may know, strings just don't want to be bent. Okay. So as I just said, the potential gain has to outweigh the price and the gradient energy. And if you do a simple estimate, you find that the critical radius for objects has to be larger than 1 over the mass of the axion inside the field. And if you take a typical decay constant of the axion of about 10 to the 12 GeV, you find that the critical radius is of the order of centimeters, which is much larger than the scale of nuclei that we see on Earth. So the gradient term forbids the axion to go to pi in nuclei here on Earth and neutrons. So there's no effects, no such effects in particle physics experiments, and objects simply have to be large enough, which is why we're going to look at stars. Okay, so kind of what is the effect of when the axion sits at pi though? So let's assume that we are in a system where exactly this happens. Once the axion sits at pi, as we've seen before, the nucleon mass is phi dependent. And when you plug in pi f here, you find that the nucleon mass is reduced exactly by this nuclear sigma term, which was of the order of 50 MeV. So the nucleon mass is roughly reduced by 5% in this phase where the axion sits at pi. Another effect is that the potential itself, once the axion sits at pi, is non-zero anymore. And this will add a contribution to any to the energy density, but also the pressure of the system that we are looking at. So kind of the equation of state that of our system, of our star, will be modified in this way, such that the energy density gains this this extra term from the potential. But so it will also affect the pressure, and this is what we are going to look at now. Okay, so very well. This was the part about the axions and properties at finite density. And now I want to discuss kind of a toy model, which is just kind of the equation of state of a free Fermi gas coupled to the axion. Okay, so a free Fermi gas of neutrons coupled to the axion is kind of described by this Lagrangian here, which I don't want to go into the details. But so we can get the equation of motion or solve the system by minimizing the action, which leads to a coupled system of the Einstein equations and the axion equation of motion. So here on top, you see that this is reminiscent of an equation of motion, and the two terms on the bottom are kind of the equations, the Einstein equations that are usually called the Tolman-Oppenheimer-Volkoff equations, but now coupled to the axion field. So these kind of equations are kind of hard to solve. So we solve them, but it's very technical. And I don't want to bother you with the details of this. So luckily, there's a simplifying limit, which is if there's a scale hierarchy, namely, if the scale of the system that we're looking at, the radius of the system, to be precise, is much larger than the wavelength of the field that is given by the inverse mass. And for the QCD or for light QCD axions, this is just given by the decay constant over this factor here, which is kind of the amplitude of the potential that we've seen before. And so this limit corresponds to the limit of a thin wall bubble in which the gradient energy becomes negligible, and we can throw out the gradient in our equation that we've seen before. And this leads to the system basically leads the system to decouple, and we can kind of solve the equation of motion, which will give us an equation of state, and take this equation of state as an input to solve the TOF equations, the pressure gravity equations. Okay, so this is what I'm going to do now. So we can find the equation of the state, the equation of state of the system by minimizing the potential energy. So we can minimize the total energy density with respect to phi and find this equation of motion here, which we can solve for phi as a function of the number density. Okay, so once we know phi as a function of the number density, we can plug this back into our total energy density and basically eliminate phi from our system, such that we can such that we get an effective equation of state, which is just the energy density as a function of the number density and the pressure as a function of the number density. And with the exactly. And so in order to get to physics, let's consider a very useful representation of the equation of state, which is the energy per particle, which is simply the energy density of your system divided by the number density. And now, if you think about a free Fermi gas of neutrons, the energy per particle as a function of the density is as follows: that at zero densities, you have just a bunch of neutrons that are separated at infinity, such that their energy per particle is just their mass. But once you kind of squeeze them together, increase their densities and their fermions, the energy that you need to put into the system increases. So this is just the case of a free Fermi gas. But now what happens in the case of our axion? So before we reach the critical density where the axion kind of goes to pi times f, the system will look exactly like our free Fermi gas. So this is this dark blue line here. So the axion sits at 0. Now, once we reach the critical density, the mass of the nucleon is suddenly reduced by 5% by this nuclear sigma term, and we enter a completely unstable phase. This is shown here as a dashed line until some density n star, where the system stabilizes again and enters this new phase here, this absolutely stable phase. And you can see that this is more stable because just the energy that we need is just much lower. And okay, so why do we have this unstable phase here? In order to see this, it's very useful to look at the pressure of the system, so that the pressure is related to the slope of the energy per particle. And now, once we reach the critical density, so in the metastable phase, basically the potential is 0 and we just have our free Fermi gas. But now, once we turn on the axion, once the axion sits at pi times f, we have a negative contribution to our total pressure that is larger than the pressure from the Fermi gas itself, such that the total pressure becomes negative. This is why we have this negative slope here. And this is in a range between the critical density and this n star here. And so now V is a constant of the density, but the Fermi gas pressure of the neutrons will increase, and at some point at the density n star, there's a pressure, there's a 0 in the pressure, and afterwards it will increase again. So if we plot this, if we plot the log of the pressure as a function of the energy density, this system kind of looks like so. You have basically a positive pressure until a critical energy density. Once we reach this unstable phase, there we have a negative pressure, so we plot it as log so you don't see it. And then we start at 0 pressure at some finite energy density and increase the pressure towards higher energy density. So this is kind of the equation of state that we get just by coupling a light QCD axions to a free Fermi gas of neutrons. Okay, so now at the beginning I told you that we are thinking about white dwarfs. So let me talk about white dwarfs for a second. So what are white dwarfs? White dwarfs are very well described by a degenerate Fermi gas of electrons and light nuclei. So the job of the electrons is basically to balance the gravity pressure, while most of the mass of the white dwarfs comes from non-relativistic light nuclei ranging from helium-4 up until magnesium. And so the energy density of standard model white dwarfs is just described by A over Z times the mass of the nucleons times their number density. And furthermore, we can impose charge neutrality, which is just to say that the number density of the electrons equals the number density of the protons. And with that, we can write down an equation of state at 0 temperature, which allows us, again, to solve the Tolman-Oppenheimer-Volkoff equations. Here, I neglected the GR corrections. But in principle, one can easily take them into account. And so once you do this, what you get is a mass radius curve. So on the y-axis, I'm showing you here the mass of the white dwarf is a function of the radius, and the black line is kind of the standard model white dwarf line by the equation of state that I just described. And the dots in different colors here are data sets of mass and radius measurements of white dwarfs that are independent of the equation of state. So these points here are, I think, from SDSS, and they don't take as an input the equation of state of white dwarfs. Okay, and so you see that in this picture here, we can describe this data kind of well. Of course, these points lie pretty far off. This is because we didn't take temperature into account, but still this, to a very good approximation, gives you what you see. Okay, and so how does this picture look if we now take the axion into account and take a axion-dependent nucleon mass? Okay, so now the equation of state is pretty much analogous to the free Fermi gas picture where we just had neutrons, but now the mass of the nucleon will depend on the axion. So before I neglected the energy density of the electrons, now I take it into account. And we have this new phase set again, so n star once, so when the axion sits at pi, we kind of get this new ground state phase once the total pressure is equal to 0 at this finite density. And similar to before, there exists a range of densities where the axion sits at pi, but where the total system has negative pressure. And what this means is that in this phase, there can be no stable configuration of stars, which in the end translates into a gap in the mass radius curve. So if we take the equation of state that I showed you before, just for white dwarfs, and solve the Tolman-Oppenheimer-Volkoff equations, what we get is what I'm showing you here. So basically, the green line are solutions to the Tolman-Oppenheimer-Volkoff equations where the central density is below the critical density. Then there's a huge gap in densities until we reach the new ground state density that was much larger, and then we enter this absolutely stable phase, which I'm showing you here in orange. And you can see that there's a huge gap between the green, the green mass radius phase and the orange one. So in this case, so for now, I took an epsilon parameter which tuned down the potential, which sets the critical density. We are predicting a huge gap in the mass radius curve of white dwarfs. So in principle, so here you cannot explain the existence of these data points. So this would then lead us to the conclusion that we can exclude this this epsilon parameter of the light QCD axion model. And now, so if we go to the axion parameter space that I was showing you before, so here we have 1 over the decay constant as a function of the mass. Here in black we have the QCD axion line, and yeah, I've shown you before some other bounds. There's the supernova bound, there are bounds from the sun and from super radiance. And so now with this mechanism that I just showed you, we can exclude this red band here, just from basically the gap in the mass radius curve by comparison to data. And okay, so the boundaries of this band are, so to the right, so for large epsilons, white dwarfs are simply not dense enough such that the axion will get sourced in white dwarfs. Here on this lower boundary, white dwarfs are not large enough such that the gradient will prevent the axion from going to pi, even though it would be dense enough. And here the new ground state phase kind of exactly looks like a white dwarf. So this also doesn't allow us to draw an exclusion. But still, we can exclude a huge region of parameter space in the axion parameter space just from this mechanism. Okay, so this was the first part. Are there any questions so far? Okay, it doesn't seem to be the case.
Okay, sorry. Can you hear me?
Yes, I can hear you.
We have one question. So
yes.
So you mentioned QC action, but your argument can be applied to also action-like particles. Is this the reason you said you have the constraint?
Yes, so basically what you need in order for this to work is just a non-derivative coupling, or in the case of the axion, a shift symmetry breaking coupling to the nucleon mass. And then this mechanism kind of works. And it has to, well, it kind of has to reduce the mass of the nucleon. So the sign of the coupling is also important, but in QCD, this just arises naturally. Such that once you're in this once your scalar field develops a profile, the mass of the nucleon is reduced, and this mechanism works.
Maybe let me confirm that your argument can be applied to any axion like particle if it has
yes.
Appropriate coupling. Okay, thank you very much.
Exactly, and in fact, we also applied this already to Yukawa-like coupling and the phi square coupling to n by n, and yeah, which will be part of the part 2 that I'm going to talk about now.
Excuse me, I want to ask another question.
Yes.
Yeah, I was very interested in your talk on part 1. So I wonder, is there any? So have you ever considered about the effects from the secant phase in this kind of scenario? And another question is there, have you ever considered about the constraint early universe? Because I mean, there may be similar effect for the.
Yes, exactly. So we thought, so let me first answer your second question. So we thought about BBN. But the densities, so if I go back to this plot here, the densities during BBN are similar or lower than white dwarf density. So the region that you would exclude would kind of lie in this region here, which is already excluded now. So you're right, in the early universe, so for example, during BBN, this could easily be applied. For example, if you change the mass of neutron and proton, or well, it's like having QCD at a finite theta angle, right? And so there you change the mass ratio of protons to neutrons, and by that in BBN you would change the helium-3 to helium-4 ratio, and there are strong constraints on this, but so it lies in this region here. And I think the first question.
And also have in mind that there will be some long-range force to make some particle gather concentrate during the early universe, because theta is non-zero, right?
Yes, exactly.
Long-range force.
Sorry?
There will be long-range force between the plasma. For
long-range force.
Neutron and neutron, let's say. So they are so between them stronger than the gravity.
So what I think is that this would not work because the early universe is quite homogeneous, and in order to get a force, you need a non-trivial profile. So I would think that in the early universe, theta or the axion would sit at one constant value, and then you don't get a force, right? So I think in order so why the long range force works between neutron stars is because in between you have a vacuum and you just have some kind of overlap of the axion profile that gives you the force.
Okay, maybe we can discuss it later. I assume that the strong CP phase is order 1 in the early universe. Then it is actually just coupled to nuclear via CP violation.
Yes.
So, yeah, that is long range force. Yeah, but yeah, maybe we can discuss that. So
yes, sure. Okay. And I think your first question was about the electron, if I got it right.
The first question was about the CKM phase contribution. It is similar to the second question. So with CKM.
Okay. Then we can discuss maybe later.
Yeah.
Yes.
Thank you.
Very good. Okay, cool. Okay, so then let me get to my second part. I don't have much time. So, okay, so the second part is about heavy neutron stars from light scalars, or as we like to call it, fat zombies in the stellar graveyard. So in recent years, gravitational wave astronomy has given us a plenitude of data. So what I'm showing you here is a plot from the LIGO and Virgo collaboration, which is called Masses in the Stellar Graveyard, where this is just a diagram of objects of binary mergers listed by their mass, and 2 dots connected by an arrow is basically, or 3 dots connected by 2 arrows is basically one event of inspirals leading to some kind of heavier object. And in astrophysics, there was kind of a region between 2 to 5 solar masses where people believed that neutron stars would be so neutron stars could not reach much higher masses than 2 solar masses, and black holes would probably be larger than 5 solar masses. So there was kind of the prediction of a mass gap, and then the question arises, okay, what are these fat zombies living in the stellar graveyard? And so kind of this is a little bit hard to achieve in the standard model, because so neutron stars, to predict an equation of state of neutron stars that reaches below 2 solar masses is hard, because once you include other degrees of freedom in the QCD equation of state, like hyperons and so on, this usually leads to a softening of the equation of state of neutron stars. Exactly. And so the question is, how can we kind of get a stiffer equation of state of neutron stars? And for that, I want to consider a very simple example, which is just again our non-interacting gas of neutrons, and we can solve again the Tolman-Oppenheimer-Volkoff equations and get the maximum mass of about 0.7 solar masses in a radius of 10 kilometers. So this is just a toy model, but it's very useful because we can make explicit the dependence of the neutron mass on these parameters. So the maximum mass of the neutron star scales as 1 GeV over the mass of the fermion, and the radius in a similar way. So if we reduce the mass of the neutrons by, say, a factor of 3, or the fermions that we take here, we get an order 10 effect in the maximum mass. So just by reducing the mass of the neutrons, we get a mass radius curve that is kind of shifted up here to larger radii and larger masses. And okay, there's also an easy argument for why is that. So at fixed energy density, so if we take a fixed energy density epsilon naught and suddenly reduce the mass of the neutron, we need more so more neutrons, so a higher number density of neutrons to get to the same energy density, and a higher number density means more pressure because they're fermions. And now we just increase the pressure relative to the energy density, which corresponds to, per definition, a stiffer equation of state of our system. So there's a very intuitive way of understanding this behavior. okay, so what kind of equation of state or what kind of model do we have in mind? So let's consider generic scalar. So this is not, you can think of this as an axion-like particle or some other scalar. With this potential here, again, we have some parameter that sets the amplitude of our potential, and a coupling to nucleons similar to as before, but now parameterized by this coupling G here, such that once, so in the phase where the axion is not sourced, we just have the nucleon mass, the standard model nucleon mass, and in the phase where the axion or the ALP is sourced, the nuclear mass is reduced by this factor G. And we take G between 0 and 1 in this case. And so the question is, okay, what kind of equation of state do we get from this mechanism? So reducing reducing the mass of the nucleon stiffens the equation of state, as we've just seen. But there's also the contribution from the vacuum energy, which, as before, we've seen that this is a positive contribution to the energy density, and this will soften the equation of state. So there are two competing effects, which kind of split our parameter space into two regions. So we can parameterize this in two cases. So one is where the potential is dominating. This is the case where the energy per particle is larger than the mass of the nucleon for all densities. And so this is shown here. Here again, I'm showing the pressure as a function of the energy density. And in this kind of coexistence phase, as we call it, we reach a first order phase transition that leads to hybrid stars with a softer equation of state. So this would correspond here to the blue line. So we experience here a kind of first order phase transition that softens the equation of state because we have less pressure per energy density. In the other region where the mass change is dominating, so this means that the energy per particle will have will be less than the standard model mass of the nucleons at some pressure, at some number density, sorry. And this will lead to a new ground state, which has zero pressure at some energy density, at some finite energy density epsilon naught, and this will give rise to this kind of stiffer equation of state shown here in red. Exactly. And so if we now look at the parameter space of this model, so on the y-axis, I'm showing lambda, the scale of the self interactions in GeV, and on the x-axis, I'm showing the effective mass. So before we kind of were limited to this light QCD axion band here in purple, because the coupling to the nucleons was fixed by QCD. But once we relax this assumption, we can really get very large objects. So the radius and the maximum mass of our star scales with the effective mass here. So the dashed lines are contours of maximum mass. So once we kind of reduce the mass of the nucleon by some kind of factor, and we have a small self interaction, then we get really objects that can be of the order of 50 kilometers and have 5 solar masses or even larger. And okay, so there's several limits. So if the self interaction is kind of 0, we go back to the limit of a pure Fermi gas with a reduced mass, which just lies here. This region here, the coexistence region, is kind of disfavored just by from the equation of state argument that we get a softer equation of state. And this would kind of the region, the parameter space where we have our fat zombies and we get our order 10 effects that kind of live here in this mass gap. Okay, and so with that, I want to conclude. So we've seen how white dwarfs probe light QCD axions. So light QCD axions can get sourced in white dwarfs, which leads to a gap in densities that eventually leads to a gap in the mass radius curve and allows us to exclude large chunk of the parameter space. And very importantly, this does not rely on the axion being dark matter, because the axion will just be sourced by the background density and does not have to be around. And in part 2, we have seen how to get stiffer equation of states for neutron stars from light scalars. So once we have a light scalar with a non-derivative coupling to nucleons and make them lighter, there are two phases. Once where the potential is dominating, then we get effects on the maximum mass. Predicting self-bound objects in this new ground state phase. And one can consider couplings to electrons, gravitational waves from first order phase transition. And also we have not discussed about dynamics at all. Okay, and with that, thank you very much for your attention.
Thank you very much. So we have time to get the questions. Okay, so I have a nice question that do you think kind of a distribution of the magnetic field around the so white dwarf could influence on your I mean, so the profile or something?
Well, so I think for a white dwarf, the magnetic field is not very large, but it would be, of course, it would be interesting, for example, in a neutron star, to see if there's some kind of back reaction from the magnetic field on the axion profile. That would be definitely interesting. I mean, it could go in two directions. It could either help the sourcing or prevent the sourcing. But no, we haven't studied this. But okay, so naively, I would still think that kind of the main or the dominant effect just comes from the density.
Okay, thanks. Okay, so we have another question from Jordan. So
yes.
Yes, hello. I have just a question on your last plot. So if I understood well, you're showing like how I suppose G is the coupling here, small g.
Yes, exactly.
And so how the coupling modifies basically the possibility of having like a higher mass neutron star, higher mass objects, basically.
Exactly.
But I suppose that G, so the coupling between the scalar field and is it like the nucleons?
Mm-hmm.
I suppose that this is very small, no? So how can you? I mean, how come would it make like observable effects? Like if you consider G to be, I don't know, order 10 to the minus 10, for example, or something like this.
No. So G, we are ranging G between 0 and 1 here.
Yeah, but I suppose like using already existing constraints, this G might be small, no? I mean, if not, we will see it.
Well, I mean, you can think about models where basically, I mean, for the QCD axion already, it's not small. So G is proportional to the nuclear sigma term, which is 50 MeV. And so basically, what? Sorry, I see your confusion. It's because usually for axions, all the couplings are suppressed by F, right? But in our object, the axion itself goes to some factor times F such that the F suppression effectively cancels out.
Okay, so then
this
it's
is,
okay.
Exactly, so this is why we have these large effects.
Okay, now I understand. Thank you very much.
Thanks. So in the chat box, Giovanni asked could magnetic fields cause the production, action converted to photons? So
yes. So people have looked into this. And so I think that you get a flux of photons that is somehow relevant, but I think for particle production, you need a time varying axion profile. And so you need kind of some kind of non-spherical axion profile. And so we have not studied this. Everything that we did was was assuming spherical symmetry. But I think it would be interesting to look at this effect. And so I know that people also from TU Munich, like Björn Gabrecht's group, for example, have looked into axions being converted into photons. Yes. Yeah.
Oh, so one question.
Yes.
Sorry, I have one comment. This is Kohei Kamada. So tomorrow I will give a talk, but I will introduce an interaction of the magnetic field and axion in the presence of in the presence of matter. So perhaps it will be relevant. So it will be great if you could hear my talk, or you can also look at my slide in the Slack.
Yes, so I'm not sure about the time difference. So when is your talk in? Yes.
So around noon tomorrow. So I'm not sure.
Oh, this will be.
I have already uploaded my slide in the Slack, so you can check it.
Okay, so I will look at your slides and then we can maybe chat over Zoom. For sure.
We're very sorry. So it's almost time is over. So let's move on to the next talk. So let's thank Konstantin again. Thank you very much.
Thank you very much. Thanks.
Okay, so let's go to the next. So the next speaker is Miguel Zumalacarregui. Sorry for my pronunciation. So we're going to talk about probing ultrawide dark matter with lensed gravitational waves. Okay, so when you're ready, so please start. So, yeah, can you hear me?
Miguel, I'm afraid you are muted.
Okay, so yeah, so if you're ready, so let's start.
Can you hear me better now?
Yes, yeah, we can hear you.
Is it the sound good?
Yeah, now it works.
Yeah, thank you. Sorry, I'm having some trouble with Zoom. Okay, so I'll be talking about mostly talking about lensing of gravitational waves, and at the end I will say how we think we can probe ultralight dark matter with this method. And if anyone has questions or wants to discuss further, please contact me on Slack, or here's my email. Feel free to reach out. So gravitational waves, the situation we have is we are observing the signals from very violent events in the universe, usually the coalescence of compact binaries, in this case, black hole, a pair of black holes of stellar mass range. And our signature is the signal that as the binaries lose energy and approach each other, they start orbiting faster and emitting at higher frequencies. So it's a signal we understand very well. And in some cases, some of these signals will be some of the sources will be located behind a galaxy or other lens. And in that case, we expect the standard gravitational lensing phenomena to occur. So these trajectories of these gravitational waves will be deflected. There might be multiple images forming, which will be then magnified and have a certain time delay. So that's the usual stuff. But in addition, because gravitational waves are coherent and have very low frequencies, we can discover and use new effects that are very difficult to observe with lensed electromagnetic radiation. And in particular, I'm interested in diffraction. Just for reminder, if we have light, in this case, a laser or coherent light, like a gravitational wave, going through an opening, we can see a pattern on the other side that carries information about the aperture and the size of this object. So in a manner analogous to that, we can use lensing of gravitational waves to learn about lenses and their properties. So I think it's interesting to look at lensing of gravitational waves because for three reasons. First is lensing of electromagnetic signals is already a very well-established probe of large-scale structure and properties of dark matter. And now we have a new messenger, so we want to use it as well. But in addition to that, gravitational waves are very complementary to light, and they have some of the weaknesses of one become the strengths of others. So gravitational waves are coherent and have very low frequencies, which will allow us to observe diffraction and other wave optics phenomena. They're also very weakly coupled, meaning that the universe is transparent to gravitational waves. So we don't need to worry about dust or other objects blocking or outshining our gravitational waves. And finally, they are very well modeled. We have a standard theory of gravitational wave emission that we do not have for most electromagnetic sources. So this is also another handle on the problem that we can exploit. And well, while the rate of strongly lensed events is expected to be small, the number of detections is growing very rapidly. So it's just a matter of time before we start seeing the first lens gravitational wave sources. Just to briefly give an overview of the what lensing does to gravitational waves. So I'm gonna be showing plots of a quantity that f of w that we call the amplification factor is the ratio of the lens amplitude of the gravitational wave as a function of the frequency divided by the unlensed. And it looks like this, and we can plot it in terms of a dimensionless frequency that it's scaled by in a manner that's given by the mass of the lens. So in this way, we can put the predictions of lenses with different mass in the same plot. And there are three regimes. So at very low frequencies, we have a perturbative effect. So you can see that this is gray line is unlensed. So we have a subtle frequency dependence. This is usually small. So here I'm showing a typical LIGO source lensed by objects of different mass. So in this case, if the lens has 3 solar masses, we this source and the time it spends in the frequency range that we can detect with LIGO would cover this red region. And here we would see a small difference in the waveform with like a slight increase of the amplitude towards higher frequencies. Now, if we increase the mass of the lens, this is for a 300 solar mass object, we are in this like wave optics, pure wave optics region in which lots of interesting things can happen. So in this case, the the span of the signal is this red region, and we see that we have some amplification, like the amplitude is modulated, then it decays, and then it grows again right at the merger. And this is, it's not a simple perturbative calculation, it's a more difficult, mathematically very interesting computation that I do not have time to describe, but you're welcome to ask me if you're interested. And then, yeah, this is, it's interesting because then this amplification factor is sensitive to the, this is the time delay function. This explores basically a large portion of the lens. So we are in principle sensitive to the whole matter distribution of the object. And then, well, as we increase the either the frequency or the lens mass, so this is for a 30,000 solar mass object, then we explore this very oscillatory region. But if we go to the time domain, this is just boils down to having multiple copies of the signal. So in this case, we have two, the original signal gets split in two. This is not different than having multiple images of the same object. If you're used to lens quasars or lens galaxies, this is basically the same, except now we are very mostly sensitive to the time delay between these two signals, which is what we can measure very well. So these are roughly the three regimes. Now let's move on to what is the phenomenology of, say, non-trivial lenses. So I'm interested in features, how to probe features of a gravitational lens. And I'm gonna be showing results for a lens that has a core. And this is motivated by ultralight dark matter and the formation of these solitonic cores at the centers of dark matter halos. So I'm not gonna, for now, I'm not gonna be doing a very realistic parameterization. This is just a simple profile that in the limit in which the core size goes to 0, this recovers what's known as a singular isothermal sphere. This is just a very simple, very common lens. And then I'm going to increase the size of this core. So in the absence of a core, I'm showing here the amplification factor as a function of dimensionless frequency. For very low frequencies, we have no lensing, as expected. And then as we increase the frequency, we have basically showing, I'm showing here. Hello? Someone? Okay. We have this interference pattern between the two images. And here I'm showing the, in the rightmost panels, I'm showing the envelope of this interference pattern. You can see that there's a little bit of wiggling. It's very subtle. This comes from wave optics corrections when the frequency is still not very high. So now let's increase the size of the core. This is at a fixed impact parameter. And what you see is, well, some subtle differences at low frequencies. But then what happens is that this interference pattern gets a secondary modulation that you can see here in the envelope. And this is because an additional image is allowed to form near the center of the lens. So we have the interference between 3 instead of 2 images. Now, increasing the core size, here the red line just exacerbates this effect. And if we push this to the limit, as in the purple line, we can make this very, very apparent. And this corresponds to, for this particular case, this impact parameter corresponds to the case where we are close to the region separating single image from multiple images, what's known as acoustic. So this is where the wavefronts intersect. And there we not only have a very dramatic secondary modulation, but also I'm showing here in dash is the prediction for geometric optics. So this standard theory we're used to. And this convergence to that limit happens only at very high frequencies. So we can do reconstruction of the lens parameters. We did this through a Fisher matrix approach. Here, I'm mostly interested in the core size, but we can measure also the lens mass and the impact parameter of the lens. This is for, as we increase the mass of the lens, we see that the constraints get better and better, but they're projected one-dimensional posteriors get saturated. So you can see here that these ellipses get thinner and thinner, but there's always this is just one combination of these parameters that gets very well measured. We can look at this for Lisa. This is plots for different so for the same lens mass, in this case is effective lens mass of 10 to the 7 solar masses, and this is different sources. So of course, heavier sources merge at lower frequencies, so we are more in this perturbative regime, whereas lighter sources merge at high frequencies, so we have this more geometric optics limit. But we can look at this, the precision that we can get on the different lens parameter. And in particular, we find that the core size, and here in this plot, this is the error expected on the different parameters. The size of the core, we can get precision that it's of roughly 10 to the -3. This is for a signal to noise ratio of about 1,000, which is what we expect for massive black hole binaries. So it's pretty precise, and this is something we can then we can go back to the dark matter predictions. And as you know, you are the experts on this. We have these models, in particular fuzzy dark matter. I'm going to compare this with the core size that is in particular this equation. This is from Hui et al.'s paper, and then we can compare this is the detectable on the gray contours are the detectable core size as a function of the lens mass for Lisa, and then I'm also showing for LIGO sources. LIGO is less accurate, but it allows us to probe lighter lenses. And then in purple is the ultralight dark matter mass that could be probed by this method. So the masses that could be excluded. And and here I'm showing this in this against this projected lens mass, but I can also translate this to, under some assumptions, to the actual mass of the dark matter halo, and this is what the potential of these observations has. And for comparison, I'm showing this constraint from ultra faint dwarf galaxies from Dalal and Kravtsov, which is a pretty one of the most stringent constraints. And if we get lucky enough with LIGO, we could, in principle, or with a ground detector, go past that that constraint. Now I just want to show my last slide. So I was focusing on a very simple model, in which I took a very simple lens and put a core by hand. We're also interested in looking at more realistic profiles, in which we have solitonic core with the shape that's predicted in M-body simulations of ultralight dark matter matched to a Navarro-Frank white profile, as shown here. And we can compute the prediction, the amplification factor in that case. And in particular here for the total profile, we get the black line, which has some interesting features at very low frequencies, kind of subtle, and then at high frequencies is more prominent. So this is something that we're looking at now, and we'll hopefully be ready in a few months. So just to conclude, I want to highlight that gravitational waves are very complementary to electromagnetic observations. In particular, we can use wave effects to probe lens properties and recover some of the lens parameters with a precision of about 1 over the SNR, despite strong parameter degeneracies. And I think this is just the beginning. We can, we're interested in taking this to more accurate model and more detailed model of dark matter structures and substructures, and use it to infer dark matter properties. So thank you very much.
Thank you very much. So, okay, we have a question.
Thank you very much for interesting talk. So the result are sensitive to the profile at the outer layer, so not the outside of the support region, so the index of the outer part.
Sorry, can you repeat?
Yes, so the result is sensitive to the slope index at outer region of the halo.
Like here?
Yes. Is it sensitive?
Yeah, so yeah, it's interesting. It's hard to see here because the blue line is it's very, so this is, I have to say, this is for a very it's a large impact parameter. So we're talking here about weak lensing regime in which we only have one image. So if we only had the Navarro-Frank-White profile, the results are pretty mild. You can see that the blue curve goes from 1 to, has a little bit of an oscillation, and then goes to a sub% magnification. Whereas if you add the solitonic core, the red line, you get the black line, which is much more dramatic. I think this is because, well, we're at large impact parameters, so we have a big blob of mass that far away looks a little bit like a point lens, not quite. It looks like a point lens. What's interesting is if we consider only the red, only the core, we have something very similar, but it's shifted to smaller dimensionless frequencies, and it's also for some reason this low frequency feature is more prominent, which I do not understand why that is the case, but somehow this gets softened by the Navarro-Frank-White outer region.
Okay, thank you.
Yeah, of course, if we decrease the impact parameter, then the situation might change. We're not looking into that yet.
Okay, so we have another question.
Thank you. This is Fumihiro speaking from the University of Tokyo. Let me ask some basic points. So first, how can we distinguish the lens waveform between an unlensed waveform? For example, so you have shown some examples of lens waveform in page 4. And so can you exclude the gravitational wave is originally like unlensed blue wave, so lensed red form without lensing?
So that is a very good question. So for example, well, there are different regimes, and we expect that there will be some degeneracies between the lens parameters and the waveform parameters. So for example, in this regime of like wave optics, So we think this will be degenerate to some extent with a precessing waveform, where you have like this, the orbital plane of because of the spin, misaligned spins between the binary components. The lens, the orbital plane will be oscillating in the as the gravitational wave is emitted, and this might partially look like this. Now it's not an exact degeneracy because there's different, the frequency dependence is different. Also, if you have precession, the orbital plane changes. This changes the ratio of the two polarizations, the plus and the cross polarization. So there's ways to distinguish both, but a partial degeneracy is with imperfect data. There's always going to be some uncertainty. Now, in this regime, in which we have multiple images, now here I'm showing a case in which the two images are separated by a fraction of a second, but this could, if the lens mass is 10,000 solar masses, as is the most typical case, then this time delay will be weeks or months. So in that case, it's actually very difficult because one needs to match different signals that seem to have the compatible sky localization and intrinsic properties. And this is quite challenging. And there's always a chance of a false alarm, just having two signals that by chance look similar enough.
Okay, thank you very much.
You're welcome.
Okay, thank you very much. So I think time is up, and so let's thank Miguel again.
Thank you.
Thank you very much. Okay, so let's move on to the next talk. So next speaker is Arianna Foschi, who's going to talk about motion of S2 and bounds on scalar clouds around the SgrA. So when you're ready, please start.
Hello, thank you. So can you hear me and see everything okay?
Yes.
Okay, perfect. So yeah, first of all, I would like to thank the organizers of this workshop for giving me the possibility of talking about my recent research on constraint that we can put on a scalar cloud around Sagittarius A star. So this work has been done in collaboration with my supervisor, Vitor Cardoso, my co-supervisor, Paulo Garcia, and the whole Gravity collaboration. So the motivation behind this work is, of course, related with dark matter research. Indeed, as you know, ultralight bosons, such as scalar fields, are possible candidates for dark matter. And moreover, we know that dark matter may cluster around supermassive black holes, giving rise to these high-density spikes around them. So in this sense, the galactic center becomes the perfect laboratory to look for dark matter, since there is a supermassive black hole, Sagittarius A star, with a mass of order 10 to the 6 solar masses. And specifically, we know, as you can see from this image, we know now the orbit of dozens of stars called the S-stars, orbiting very close to the galactic center. And since the gravity instrument has been put into operation in 2017, we are able to know the position of these stars with a precision of order 10 to the -6 arcseconds, so with a very high precision. In this work, we focus on the motion of star S2, which is represented in this orange circle, which is one of the closest stars to the galactic center, and it has been monitored for more than 30 years now. So we have collected data for 2 entire orbits. Together with these astrometric measurements, so the position in the plane of the sky, we also have available radial velocity measurements, which is the total space velocity of the star projected onto the line of sight. So several works in the past have used the motion of stars to obtain constraint on possible extended masses around, say, J star, so to gain information about the environment of this supermassive black hole. For instance, the gravity collaboration has used a Plummer profile for density distribution, and they were able to put an upper bound of order 10⁻³ the central black hole mass on the extended mass described by such a profile. In this work, we considered a different setup. We start with a massive scalar field minimally coupled to gravity, where the mass coupling alpha is defined in this way. And in the limit of small coupling, we can solve the Einstein plus Klein-Gordon system of equations and get an analytical expression for the fundamental mode of the field. Here, the amplitude of the field is related with the fractional mass lambda, which is the ratio of the mass of the scalar cloud over the mass of the black hole. And in particular, this is the parameter that we are interested in fitting. Such a profile gives rise to a scalar cloud which has a toroidal shape, as you can see from this image. And once that we have the scalar profile, we can get the energy density from the 0,0 component of the stress energy tensor in the non-relativistic limit, so neglecting terms of order c to the -4. With the energy density, we can solve Poisson's equation and get an expression for the potential generated by the scalar cloud. And this potential can be added in the Lagrangian to the Newtonian potential m over r induced by the central mass. So the system so constructed basically described a Newtonian, perturbed Newtonian model. However, there are some effects that we need to include to somehow correct our model and get a better fit for our observational data. In particular, we include the so-called Romer delay, which is the difference between the observational dates that we have and the actual emission dates of the signal, which is a Newtonian effect and is simply due to the finite speed of light. Moreover, this Newtonian approximation is well posed for the motion of S2 that orbits quite far from the central black hole. However, near the periastron, it reaches a total space velocity of order 10 to -2. So in this region, relativistic effects become particularly important. For this reason, we included also the relativistic Doppler shift and the gravitational redshift. And finally, since the Schwarzschild precession has been detected in the orbit of S2 at 8 sigma confidence level by the gravity collaboration, we also included the first post-Newtonian correction to the equation of motion, where this parameter FSP quantifies the magnitude of this contribution, and it is set equal to 1 throughout this work. So this is the model that we are going to fit our data with. And as a first step, we start with a simple chi-square minimization. And here in this plot, you can see the results of this analysis, where I reported the best fit values for lambda as function of alpha. As you can see, the uncertainties on lambda are quite large, except for the range of the couplings roughly given by 0.01 and 0.03, where the uncertainties become much smaller. This can be understood looking at the effective peak position of the density distribution, so of the cloud, that scales as alpha to the -2. And it is represented by this gray dashed line. So in this region, this is telling us that the S2 that the cloud has effect on the orbit of S2 when the star crosses regions of higher density, meaning when the cloud is located as its peak between S2 periastron and apoastron. In the other cases, when alpha is smaller, the cloud is located far away from S2 apoastron, and so the density inside the orbit is too small to affect the motion of S2. Vice versa, if alpha is large, the peak of the cloud is very close to the central mass and it becomes degenerate with it. So it is extremely difficult to separate the two contributions. So now that we have an idea of what to expect, we can move to the second step, which is applying a Markov chain Monte Carlo method. In particular, we use the MC Python package developed by Foreman and collaborators. So the idea here is that we want to sample the posterior distribution of a set of parameters given a certain data set, and this by Bayes' theorem is proportional to the likelihood of the model times the priors that we impose on the parameters. We performed this analysis several times for different fixed values of alpha, and each time we fitted for the following set of parameters: the 6 Keplerian elements describing the orbit, the galactic center distance, and the black hole mass. 5 additional parameters that are not really interesting, physically speaking, and basically they are only useful to merge two different data sets. And finally, we include the scalar field fractional mass lambda. We used a Gaussian likelihood for our model and uniform priors on all the physical parameters involved. The offset parameters instead are described by, we use the Gaussian priors for them because their estimate come from a different experiment and different data sources. So here I report the results of the MCMC analysis. This basically confirms what we already seen in the chi-square minimization analysis. Indeed, you are looking at the marginalized posterior distribution of lambda for different values of alpha. And here we are looking for the maximum likelihood estimator for lambda that we call the lambda hat, which represents the value of lambda that maximizes the likelihood. Since, as I said, we use the flat priors, in this case, the posterior basically coincides with the likelihood of the model. So we are dealing with basically two kinds of distribution. When we are in the interesting range of alpha, so when the cloud is peaked within S2 orbit, the distributions are basically Gaussian, and the maximum likelihood estimator can be estimated via the mean of the distribution, and the uncertainties are given by the standard deviation. However, when the cloud is located far away from S2 apoastron, the posterior starts to be peaked around 0, which become our maximum likelihood estimator, and we estimated this 1 sigma confidence interval, so this orange band that you see represented here, looking for that value of lambda such that roughly the 68% of the posterior lies below that value. As you can see from this table, where I reported the 1 and 3 sigma confidence interval, when the cloud is located far away from S2 apoastron, we can only obtain a very broad range on lambda, so this is not really meaningful. While when instead the cloud has these values of the coupling, we found always a non-zero value of order 10 to minus 3 with uncertainties of the same order of magnitude. So in order to test the significance of our results, we computed the bias factor, which is the ratio of the likelihood of the model computed with those values of alpha and lambda, over the likelihood of the model when lambda is equal to 0, so the non-perturbative one. According to Castel-Raftery, there is a decisive evidence that the perturbative model is preferred over the non-perturbative one only if log k is greater than 2. And as you can see from this table, we never found log k larger than 2. And this information, together with the fact that all these values of lambda are compatible with 0 within the 3 sigma confidence interval, made us conclude that there is no evidence, not enough evidence to claim the presence of such a cloud. However, for the first time, we have the values of the couplings of a scalar field that can be constrained using the motion of S2. And for those values of the coupling, we found an upper bound of order 10 to minus 3 for the extended mass of the cloud. So just a few words about the formation process of the scalar cloud. We have been agnostic about it during our work. However, we know that fluctuations of massive scalar field can be exponentially amplified by superradiance mechanism. So if the cloud extracts rotational energy from a spinning black hole. However, Kodama and Yoshino showed that for a supermassive black hole with the mass of Sagittarius A star, the effective mass of the field must be greater than 10 to the minus 18 electron volt in order to engage a superradiant instability in a time scale that is smaller than the age of the universe. This value of the effective mass corresponds to the very upper bound that we can actually test with S2, which corresponds to alpha 0.045. And so if such a cloud exists, then it is very unlikely that is formed by means of superradiance. So there should be some other mechanism explaining it. However, one possible explanation is that the dark matter halo, the dark matter distribution existed by itself in the galaxy, and a black hole can acquire these long-lived structures around it that resembles those of superradiance, simply passing through this dark matter distribution. This has been shown in 2 recent work of Cardoso and collaborators. So to summarize, we use the astrometry and the radial velocity measurements of S2 to constrain the fractional mass of a scalar field cloud around Sagittarius A star. The orbital range of S2 only allow us to constrain meaningfully values of decoupling between 0.01 and 0.045. And for this range of decoupling, we found an upper bound of order 10 to the minus 3 for the fractional mass of the scalar cloud at 3 sigma confidence level. So I would stop here and thank you very much for your attention.
Thank you very much. So, any question? Okay, so I have a question. So I may miss your point, but so what kind of prior probability distribution did you assume to get the result from the MCMC simulation?
We used basically flat priors. So sorry. So for instance, we just set, so we had the previous estimates of these parameters from previous gravity works. So for instance, we choose, I don't know, for the eccentricity, the previous estimate was 0.88. And we put a bound of between 0.8 and 0.95. So we just put some ranges, some possible ranges for those parameters, for all these parameters.
Okay, thank you very much.
You're welcome.
We have another question.
Okay.
Thank you very much. This is Fumihiro speaking from the University of Tokyo. So please go back to the slide of motivation. Maybe I might just miss to catch up, but why did you focus on only S2 stars?
Because S2 is the star that has been monitored for the longest time. So all the other S stars only had very recent measurements, while for S2 we collected 2 entire orbits. So we simply have more available data. However, we also we are also planning to extend this analysis also to other S stars.
So if you can extend this method to other S stars, will you extend the range of alpha?
Yes, possibly yes, because other stars orbits in different orbital ranges. So they would allow us to test different values of decoupling because of the effective peak distribution of the cloud. So each star will have its orbital range and its value of decoupling that can actually test. So this would allow us to extend the range overall.
Okay, thank you. And the final question is, in the picture of the motivation slide, the precision of this observation is maybe very 0.1 arc-sec level. So is it required to do some the most powerful telescope with adaptive optics in the in our techniques to increase the data of other S stars?
You mean using adaptive optics to improve the measurements? It is already used in the gravity instrument. It is an adaptive optics instrument.
Okay. Thank you.
You're welcome.
So, any other questions from people in Zoom? No? Okay, so I think time is up. So let's thank Arianna again, and let's thank all speakers. Thank you very much.
Thank you.
Okay, so before closing this session, so I have